1 2 1 2.
Yeah.
So now this is the master.
Yeah.
But if I PFL anything else,
Yeah,
then now this is
All right, welcome everyone. My name is Martin Maas. I'm a research scientist at Google DeepMind. I'm the general chair of ISMM, and I want to welcome you to the conference. We have a great program today. We'll start with welcome and keynote by John Kim. We'll have a coffee break, then a second session, then lunch. Then we have another keynote by Eric Österland, and then we have once again coffee and another session. So this is the 24th installment of ISMM. And it is the second ISMM that has an expanded scope that includes not only programming languages, but is explicitly extended to include the computer architecture and systems community. And one way this is reflected in the way we run ISMM is that we now have a dual chair model. Tim Harris and Onur Mutlu are the program chairs this year. And we're basically covering not only programming languages, but all aspects of memory management, including computer architecture and systems aspects of it. We're seeing that reflected in the submissions, as you'll see throughout the program. But I think we still need to get the word out. So if you're active in the computer architecture and systems communities, please reach out to your colleagues. Let them know ISMM is explicitly looking for work across all of these communities and is interpreting memory management very broadly. Before we dive in, a big thank you to a number of people. Special thanks to Gil Hoer, who's the PLDI General Chair, and has really gone above and beyond to host ISMM at PLDI, where it's hosted every year, and to really make this a success. We also want to thank Jung Kim, who's the local arrangements co-chair for PLDI, who helped a lot with local arrangements. We thank the SIGPlan AV team for all the fantastic work. And also the PLDI web co-chairs for maintaining the website. And with that, I'd like to hand it over to Tim, who will talk about the program.
Great, thank you, Martin, and of course, thanks for all of your work in helping things go so smoothly. It's been a pleasure working with you and with Honor over the last, I think if I measured it in months, it's about 9 months since we were first talking about ISMM. On another metric, it was 382 emails ago, according to my Gmail inbox. So I'll just mention a little bit about the selection process this year. We had a great PC with 21 participants. And I think roughly the same number I see at some much, much larger multi-day conferences. The fact that a lot of people have interests in different areas and published at ISMM, have submitted this year. And we had really good response rate to people that we invited to be on the PC. And the fact that we were able to say with so many members that the reviewing load would be only 3 or 4 papers per PC member, I think really helped attract good people getting involved. We advertised for regular research papers and also intellectual abstracts where maybe the evaluation isn't yet in place, but the idea is great to publish. Practitioner reports on work describing the application of ideas in large systems, as well as survey papers as well. We received submissions in intellectual abstracts and practitioner reports. We have both of those represented in the program today. And I think that's a great way of showing that we value as a community these kind of publications that can often be difficult to get out there. We received 16 submissions this year, roughly in line with last year's ISMM, and we accepted 10 papers, 4 with some very quick shepherding within the short turnaround time that we have in the review schedule. We were able to spread the reviewing load and have 3 to 5 papers, 3 reviews per paper, averaging more than 4. So I'd like to thank the program committee, a broad range of institutions and locations represented, as we strive to do each time, and the steering committee for their input over the last few months as well. The proceedings should all be online now with the start of the conference. One final thing I'd like to mention: we have a best paper award, as is traditional just recently at ISMM. And I'm pleased to announce that this will be awarded to the paper on arborescent garbage collection, dynamic graph approach to immediate cycle collection. So we have a few certificates here, which if we have one of the speakers here already, I can provide now, and if not, then we'll present these later in the session when the paper is being delivered. So the first presentation we've got this morning is the first of our invited keynote talks. It's my pleasure to introduce Professor John Kim from KAIST. He'll be very well known to people who publish at places like ISCA and Micro and ASPLOS, an amazing set of publications in these venues, influential work on areas such as interconnect design and the Dragonfly topology. Also a great breadth of publications. I was looking at your work and seeing Kai and CSCW, computer-supported collaborative work as well. But I think today Professor Kim is going to be talking about areas closer to our memory interests, on accelerators, NPUs, specialized compute devices. So, thank you very much.
Thank you for the introduction. Is this working? So thank you for the introduction, and thank you for inviting me. I wish I would have seen Martin's slides before, because I was somewhat nervous because I'm supposed to speak at a memory management conference with a computer architecture background, so I was kind of worried, but I would have been less worried if I had seen Martin's slides. But having said that, again, thank you for inviting me, and I'm not organizing the conference, but I guess since I am based in Korea, I would like to welcome everyone to Korea. I don't know if you noticed, but the weather is going to turn really bad sometime real soon, because the rainy season is starting soon, so hopefully you'll miss that before you go back home. Now, as you probably know, the conference is being held in Seoul, and I sort of sarcastically tell foreigners that, again, Seoul is a metropolitan city, right? It's like New York, any other cities you've been to. But if you drive about an hour out, you'll really hit the countryside. So you'll see the rice paddies and so forth. And I joke that right behind the rice paddy, you're going to see a DRAM paddy, and they're going to make all sorts of DRAMs out there. Why do I say that? I don't have a strong background in memory, even from an architecture perspective. But having been in Korea for 15 years, I sort of feel like I know a lot about memory. Having worked with the industry folks, you sort of, by osmosis or something, you just sort of have a feel for knowledge of different aspects of memory. And for the next 30, 40 minutes, I'm going to try to act like an expert in memory. So we'll try to do that. And come from it from a different perspective than most of you probably come from. So I come from more of an architecture, more of a technology perspective. So hopefully I'll give you a different perspective to think about. Now, for a talk like this, I really don't like to summarize papers and give you summaries. I think you guys are all smart enough to read papers. So I'm hoping to give you at least a few things to think about or chew on, especially given that a lot of you probably come from different background as well. So recently I've done some work in PIM. So I originally titled this PIM memory management, but again, that sounded a bit too boring. So for the past couple of days when I was trying to update the slides, prepare the talk, and I sort of try to change it to domain-specific memory management. I still don't know what that means, but it sounded cool. So I sort of came up with that name, but I'll try to explain where I'm coming from. Now, I'm not going to have any fancy slides about AIs and all the importance of transformers and so forth, but I'm going to start with a very traditional computer architecture slide. If you've taken a computer architecture class, you've probably seen this. We live in an era of domain-specific architecture, right? We're designing chips to be more specific, and you see these sort of scope of different type of architectures out there. So you have CPU on one side that provides you with the highest flexibility, and on the other end, you have ASICs, or domain-specific architectures that provide you with the least amount of flexibility, but the highest amount of performance. Again, your NPU, TPU, various different accelerators would fall under this, and then you have GPUs, FPGAs in the middle, right? Again, I don't think this is anything new, but again, this is where people refer to as domain-specific architectures. You're designing architectures for a particular domain. So having said that, again, this is for the processing side. Now, another thing you've probably learned in computer architecture is that there are three aspects of computer architectures, right? There's the compute part, the one where you actually operate on the data. Then there's the memory where you're storing the data for use at a later time. And then there's a third component, which moves the data between the various different components on chip, off chip, and so forth. My area of expertise, or where I focused on, is the third aspect on the bottom, the communication. So that's where my expertise lies. But recently, I've worked in the other aspects, and I'll try to touch upon how these sort of impact sort of the memory architecture, memory design. But since, again, my focus has been on the communication, I just wanted to share this one particular slide where I would argue that networks today are also falling under this realm of domain-specific architecture. Right, you have different types of networks out there, and again, domain-specific networks is something that we just put together as a terminology for one of our papers. But you have general-purpose networks, think Ethernet, and then you have networks that are designed specifically for particular systems. For example, Google TPU has their own custom interconnect that's designed specifically for their systems. It's obviously not flexible. It's not going to work on your CPUs, but it gets the job done in terms of their particular systems. So that's where I'm coming from, and I'll briefly touch upon this later on when I talk about some aspects of PIM. But again, I don't think I need to tell people here what PIM is, right? Again, it's this notion of you moving the processing to the data, different granularities of PIMs, and so forth. So again, I sort of try to, in a cartoon, highlight different types of PIMs that are out there. But again, I don't think that's really important for this particular talk. But one aspect that is that I'm sure you've heard that PIM is not a new type of an architecture. If you go back to the 60s, 70s, that's when the first sort of notion of PIM came out, when people were suggesting you put compute inside the memory. Now, those similar ideas were revisited about 20 years later. This was in the mid-90s. But surprisingly enough, PIM has sort of re-emerged 20 years later. And now this time, I think it's a lot more serious, right? You have memory vendors actually building PIM products and different companies sort of trying out PIM architectures. So the question is, well, what is different today than 20 years ago? I think one can argue is this sort of the domain-specific aspect of it. I think there are key architectures, key applications that are requiring particular performances, bandwidths from the memory systems. And that's where I think you're seeing a lot more interest in this sort of what people call PIM, what I'm going to refer to here as domain-specific memory. So if you look at the actual publication, that presentation from Hynix a couple of years ago on their PIM architecture, they actually use that word domain-specific memory. So they used all the buzzwords, I think, in their title, memory-centric computing, and this notion of domain-specific memory. It's domain-specific memory because their memory architecture is good for just one thing, which is just sort of a GenV sort of an operation. That's it. But again, it excels at that particular operation, so it's something that's worthwhile. So given this notion of domain-specific memory, and if you go back to the first slide of domain-specific architecture, I think you can actually draw out a domain-specific memory sort of a spectrum. So again, this is something that I sort of drew together, put together myself, so I'm not sure how valid this is, but on one end, you have sort of the general purpose memory, right? You have your GDDR HBMs. And on the left 4 is actually different types of PIMs that have been proposed. And I've purposely laid them out in this particular order because they provided various different trade-offs in terms of programmability versus efficiency. For example, the Hynix PIM on the right is very dedicated in terms of functional units and has no programmability. On the other hand, ISMM, which is a type of a PIM that has been proposed, actually has a programmable core with a 14-stage pipeline. And then you have the Samsung PIMs in the middle, which provides some amount of programmability, a lot more than what the Hynix provides, but it's not as flexible as a general purpose core. So again, that's sort of the spectrum of what you have in terms of different types of memory. Now, while I was preparing for this, I obviously went to last year's conference and looked at the proceedings and the keynote. And the keynote last year was actually someone that actually knows about memory, someone that knows about PIM, a speaker from SK Hynix who talked about the details of their PIM architecture. So fortunately, I'm not going to go into the details of what the PIM architectures look like. I highly encourage you to sort of look at it because he provides a very good overview of what the architecture does, what they use the PIM for, and so forth. But having said that, again, I was sort of watching through the video, and it was very hard not to notice the last slide. The speaker throws out various different issues in terms of the challenges that they face in terms of PIM. So again, you see the memory hierarchy, where do you place the data, sort of the traditional questions that you see. Now, while I was sort of staring at this, I couldn't help recall a session that I attended about 6 years ago. This was a conference called DAC, so it's a design automation, but deals with computer architecture aspects as well. There was a speaker from AMD that we invited for a special session, and he talked about sort of data placement, NUMA awareness across the entire system hierarchy. And if you sort of stare at these two slides, they're actually very similar. Well, I guess you have to turn them upside down, sort of. But in terms of the issues that's being addressed, it's very similar. So the question is, well, what is different today and what has changed, or maybe what has not changed, right? I think over the past 6, 7 years, what you can argue is that the technology has advanced significantly. But in terms of how we manage the technology or the architectures, maybe we haven't advanced as much. So I think that's maybe something to think about, given that these sort of two presentations were made about 6 years, 7 years apart. Having said that, here's sort of the outline for the rest of my talk. I've talked about sort of giving you an introduction into domain-specific architectures memory. I'll talk a little bit more about PIM architecture challenges and the way I would like to view PIM, which is in terms of PIM as a memory and the sort of the common terminology that everyone here knows, which is locality. I'll introduce a little bit about sort of some of the work that we've done in terms of domain-specific memory management, in terms of how you use that, how it's needed for different types of architectures, and wrap up with a few summary challenges. Now again, given that this is a talk about PIM, I'm just going to give you a quick tutorial, 1-minute tutorial in terms of what PIM architectures look like. And again, because of the fact that ISMM is publicly available and many of us use it for research, I'm going to talk about that because we've also published papers with this. So again, if you look at a traditional host, it has its regular DIMMs on the bottom. And on the top, it has a separate dedicated PIM, PIM-enabled DIMMs from ISMM. And if you look at it carefully, it's organized hierarchically. So you have within a DIMM, you have 2 ranks, and each rank with 8 chips. And within 8 chips, you're going to have 8 banks. And now, up till at this point in time, the organization is very similar to any sort of memory. Now, the key difference here is that within each bank, it has its local memory. In this particular case, it's shown here as an MRAM with 64 megabytes. But you'll also notice there's what's called a DPU, which is a data processing unit, or DRAM processing unit, which is for the actual computation itself. And then you have a scratch pad memory called the WRAM. So this is a architecture that was proposed, again, by a French company. And many researchers actually use this because of the flexibility it provides, and it's readily accessible. And again, we've published paper using this system as well. But having said that, I think it's really worthwhile to look at where does PIM stand today. Again, I think that this was proposed about 5, 6 years ago, and various different PIM systems have come out. With all due apologies to the second speaker, who's going to be talking about a garbage collection based upon an UMM system. I don't know if the speaker notices, but UMM has closed down. This is, if you go to their website, this is what you'll see, and you can't get access to any of the links. So again, I don't know the internal details, but I believe this was announced within the past 2 weeks or so. So this is very recent. There's another company that was doing sort of PIM-related, more in terms of SRAM type of architecture, called Untethered AI. And you'll notice they haven't done too well. This is also announced within the past couple of weeks as well. So again, I guess timing is everything. It wasn't too great for preparing for this particular talk. But having said that, I thought I would have some fun with this. We all use ChatGPT, and given the state, I asked ChatGPT to write a eulogy for me. And this is what it had. This is really fascinating. Again, all of you have used this ChatGPT before. The only thing I edited is the highlight, because that's the part I wanted to read. Surprisingly, the bold part is something that ChatGPT thought was worthwhile. So again, it talks about that dare to ask, what if your RAM had opinions? Actually, I'm not a native English speaker, so I couldn't figure that out, so I had to follow up and ask them. And so for those that are not aware, it means if you have an opinion, you're thinking. And that's what the sort of the sarcastic joke here is, that they were trying to get the RAM to think, which is what the PIM is effectively. And then it talks about how UMM promised to transfer data-heavier workloads and perhaps confuse a few system integrators along the way. Again, I asked it on purpose to write something sarcastically, but I think it was really on the point. And the last line here is really interesting. Like many brilliant ideas in computing, UMM hit the silicon ceiling known as the industry of adoption. Again, I don't think that's a common word we use, but that's what it said. Here is the part I think that we should all be sort of aware of. While they built it, and again, this is perhaps the only PIM that academics can actually use, the industry mostly shrugged. Turning out people to rewrite their software stack, compiler tools, and mental models was maybe a bit much, right? And it talks about you were ahead of your time, slightly to the side of the market, and you have to, again, apologies to the second speaker, it may be gone from the lab, but you live in the 43 PowerPoint decks and a dozen PhD dissertations. Again, I don't mean to be rude. I was just trying to have some fun with it, and I think that ChatGPT did its job writing a sarcastic eulogy. But it does point out some of the key aspects here, right? It's a cool tool. It's a cool toy, right? But that does not mean it's going to be widely adopted by the industry. So the question that I asked myself, again, I have very limited PIM knowledge. Again, I've never designed a DRAM in my life, but again, I've done some work with PIM, and I've done some work with computer architecture in general. And I think if you leave this talk with anything, I would suggest you sort of think about this particular question. Again, you all know what a PIM is. PIM is the processing in memory. You're bringing compute to the memory. Now, when you bring a compute, again, you accelerate something into the memory. Now, what you have, is that an accelerator or is that a memory? Right? I think that's sort of a fundamental question that needs to be answered, and maybe that has been a problem, right? So I've drawn some cartoons here on the bottom that sort of tries to illustrate it, but here's sort of another interesting story. So when we first started working with this UMM architecture, obviously, as a professor, what do? You tell the students, go learn about this and tell me about it, right? And they started learning how to program it. And again, UMM had this entire software stack where you could actually run code on it. But after about a few weeks, after the students sort of got used to programming the UMM PIM architecture, he comes back to me and says, this feels a lot like CUDA. Right? Which was sort of a surprising statement, but he was, I think, right on, in the sense that the way we've treated the PIM architecture is as like a GPU, as an accelerator, right? And again, it's great because it gives you all this sort of compute and it gives you this increased amount of memory bandwidth, which is all great. But is that really going to sell? Again, I'm talking more from a sort of a business perspective. Again, I'm not coming from the industry, but I think this is something that needs to be considered. You're taking up real estate when you're plugging in these devices, right? You're actually taking away real estate for memory capacity. I think this is a well-known issue, but Samsung had an HBM stack with PIM implemented on top, which is great. It did a lot of it had a lot of cool features, but it ripped out about 1/3 of the memory capacity per layer. Now, given that one of the biggest challenges of HBM is memory capacity to begin with, right? This is not something that's going to fly with a lot of the customers, right? So the fact that you're putting these sort of expensive accelerators, well, does that really make sense, right? And again, this is my own personal opinion. There's been a lot of great research in terms of PIM over the past 5 years within our community in terms of computer architectures. However, I would argue that all of these work treated PIM as an accelerator. Now, again, if you have an accelerator, if you're talking about a TPU or NPU and all these sorts of things, they view that as an accelerator. But when you're trying to touch upon a PIM architecture, well, is that really an accelerator that you would want if you want to accelerate something? Or would you really rather go to a sort of a TPU-like architecture? If you really wanted something like this, I would argue that you want to consider this more as a processing unit or as a memory unit. Right? So that's sort of the question that I sort of pose to people here to think about. Right? Again, if you're expecting an answer from me, I don't have the answer, but I'll share you my opinion is that PIM really needs to be viewed as a memory. It's a memory that can do functionalities. It can do computation near memory. But if it's viewed as primarily as an accelerator, that's a lot of wasted memory. And I don't think, given the importance of memory bandwidth and memory capacity for a lot of these workloads today, you're not going to see a lot of customers too happy with that. Again, a lot of this is just my opinion based upon some of the work that we've done, but again, PIM should not be viewed as here as an accelerator. Again, this makes for cool research. And you can argue that you have about 1,000x improvement versus alternatives. That's great, but in order for PIM to be a much more viable technology, I would argue that it has to become more viewed as a memory. And I'll talk a little bit more about what I mean by that. So I'll try to dive into some of the work that we've done in terms of looking at how we should view memory sort of organizations, including PIM. Now, I'm going to go back about 10, 15 years ago when we did some work with a new memory technology back then. It was called what's called a hybrid memory cube. So it was a 3-stacked memory with high-speed IOs, high-speed SerDes that allowed you to sort of daisy chain these together as well as connect to various different hosts as well. Again, this was a cool technology that lived for maybe a few years, just long enough for this particular student to graduate, I think. But it was an interesting technology back then. Now, what it enabled is that systems back then were built in this sort of a fashion. You have CPUs host with its own memory and then a network. This is what we refer to as sort of a processor-centric. Now, given that the fact that these memory modules have networking capability or IOs, SerDes, you can actually connect them together and form something what's called a memory-centric organization. So what we did was, again, we proposed various different systems back then. This was a multi-GPU system back then. You could have a system where you have multiple memories, multiple memory interfaces. You have links connecting the GPUs and then PCIs together, right? But can we do something better with this because of the fact that you have so many interfaces? And this is what we proposed back then. We proposed this notion of what we call the unified memory system, where you have essentially memory pools sitting in the middle, right? So you're viewing the entire memory as one sort of blob of memory, which is shared by the various different hosts. And we refer to this as sort of what we've called a memory-centric organization. Now, having said that, I think technology has changed such that this sort of architecture is being revisited with this notion of CXL and so forth. why do I bring this back? Sorry, I'm going to skip this just for lack of time here. I'm going to try to tie this into how we should view PIM as well. So this was a work that we did where we were trying to accelerate LLMs inference. And if you look at the details of how the workload itself, you're going to have compute-heavy work components, which is effectively matrix-matrix multiplications. And then you have memory-intensive workload kernels, which is matrix vector multiplications. Now, domain-specific architectures such as the systolic arrays or TPUs are great for the matrix-matrix or the compute-intensive. And then you have the PIM for the memory-intensive kernels. So given the trade-offs there, well, wouldn't it be the best of both worlds if we could combine the two, right? So that's the work we did. And when we did this, it was done in collaboration with Hynix, which had their own PIM architecture. And then there was a startup in company, which was purchased, bought out, that had their own NPU. So we were combining this again. You have the cost-efficient architecture for the compute part, and then the PIM for the memory-intensive part. So the first architecture we could come up with is something like this, where you have the host, in this case the NPU, it's connected to the PIM, but the host, in this case the NPU itself, also needs its own memory. So that's sort of what we call the partition or the dedicated memory sort of an approach. Again, this is great because you could let the PIM run in parallel. You could let it do its compute while the NPU does its job while accessing its own memory, right? So it's the good thing about this part is that you could maximize parallelism. But you notice you have your standard DRAM, again, which is the memory for the NPU, but the PIM itself is also memory. You're essentially throwing out half the memory to use the PIM as an accelerator. Now, the other thing about these workloads, again, for the models that we use, there's quite a bit of sharing of the data. So again, I encourage you to read the paper itself, which was published in ASPLOS last year. Depending upon the models you use, you have quite a bit of memory data that is shared. What does that mean? You have quite a bit of data movement between the PIM to the NPU to the standard DRAM and back and forth, which is really not the most efficient usage. So that's not only bandwidth over it, but there's, again, significant impact on the memory capacity itself. So the proposal here was, we called it IANIS, which was standard for integrated accelerator, which was to combine this notion of PIM and the NPU together, right? So this is what was proposed as part of this work. Again, where you have sort of the PIM and sort of the host memory sitting together on top of each other. So again, we've drawn this sort of in this sort of a cartoon fashion. But what this really means is that the memory of the PIM is used for not only the accelerator, the compute part, but also for the memory for the NPU itself, right? So you don't have to copy the data over. And obviously, you get better usage of the memory capacity as well. And if you're really counting, all of the DIMMs now could support PIM, so you actually get more throughput or flops as well. Did I do that? So again, we called it IANIS because it was an acronym, but it still represents a god that had two faces. So it's sort of an analogy to the fact that the memory PIM device could serve as both a memory and an accelerator. But we did not have to have a partition sort of a system, right? A partition memory organization, but we were able to have a unified sort of an organization. Now again, I'm skipping through all the details of the papers itself, and you can find all the results and the details there. But what we were able to propose is, again, a domain-specific PIM plugged into a domain-specific architecture to effectively create a domain-specific system. But again, just plugging that in and using that obviously has its challenges. So we had to come up with new ways of scheduling. We ended up calling it PIM access scheduling, because if you look at any sort of CPUs, GPUs, you'd have what's called a memory access scheduling for the commands going out to the memory itself. On top of that, you have to also schedule the operations on the PIMs itself. So that's sort of the changes that's required for the PIM itself, or in terms of the memory management. So again, that's how we should be viewing PIM itself. But again, if you talk about memory management, If you talk about memory hierarchy, it's really hard to not talk about locality, right? Again, I think that's the first thing you learn. But surprisingly, that word has been missing in PIM. You never hear this notion of PIM locality. What do I mean by that? Again, I've shown here various different PIM architectures that have been built, and you have different units of granularity, but I'm going to call it a node here, which is the granularity of memory and the compute. Now, if you look at HBM PIM, it has 16 megabytes, 32, 64 megabytes, and so forth. What that means is that the compute can only access its local memory. What that, again, means is that if you're trying to access data that's on a different neighboring bank, then you have no way of accessing that. Actually, you do have a way of accessing that. You just have to go back to the host. So obviously, that introduces a significant amount of overhead. So you don't have the ability to do this. I try to avoid having plots, but I guess I have one here. We've run this experiment on ISMM system where we looked at a couple of workloads. The details of the workloads are not really important, but you'll notice for any sort of scalability plot, you want something linear. And we do get that for these sort of kernels if we're just looking at the compute part, right? But if we look at the overall performance of these two workloads, again, these were just two that I'm just showing here, it's not going to be the case. So the question is, why is that the case? It all comes down to, I would say, data movement, right? You have to move data between the PIMs. You have to do communication. But again, most of these architectures, PIM architectures, do not support that. So here's sort of a simple cartoon that sort of illustrates the problem that we're talking about, right? So you have the communication first, where you take the data from the regular DIM and you actually have to copy it over to the PIM itself. And then you're able to do the work on your local data. And again, as long as you're working on local data, that's fine. You're going to get great throughput in terms of compute as well as high memory bandwidth, right? But at some point, if you need to access data from a neighboring DPU, right, there's no way of actually grabbing the data from the neighboring. And there's this notion of what I refer to as sort of PIM locality. You only have access to your memory bank, which in many cases is 32 or 64 megabytes. Again, obviously for some workloads that's sufficient, but for others that's not. Especially if you have to do, let's say, a collective communication between the different compute units. So again, modern PIM systems actually do support communication, but again, it has to go through the host and then has to come back and be copied back over. And then you can actually do the processing itself, right? So you notice there's quite a bit of significant overhead if you have to do a PIM to PIM architecture. So again, this is the same, on the left is the same plot that I've shown you earlier. If you look at the overall speed up, just not the compute speed up, what you'll notice is obviously the performance starts to get worse, right? Again, this is why, because of the communication, which is shown here on the right. The next plot is a lot more interesting. This is where the overall speed up actually starts to degrade because of the significant amount of communication that's required. Right. So for this particular example, actually we needed to do some form of reduction between the data that were gathered. And because of the amount of data that you actually have to collect at the host itself, you'll notice that for 1,000 DPUs or 1,000 cores here, the amount of compute was actually a small fraction. And the majority of the time was actually spent on the communication itself. So again, to address this, I think we need both a architecture and a software solution. So this is what we proposed as part of this work, but which was a domain-specific interconnect. Again, I come from an interconnection network background, so what I try to do is, can we implement something that's specific for this PIM architecture? Something simple enough that could be done within a PIM DRAM constraint, yet expand the locality that was a problem. Now again, we're not the first to actually put it in wires. So the picture on the left is a block diagram of a Hynix PIM architecture. And you'll also notice this red lines that I've highlighted here, which is what's effectively connects the central buffers to all the local buffers as well. So it's effectively a simple broadcast buffer. What we're sort of proposing as part of this work was make that into a network where you allow communication between the various different PIM nodes. Given the time constraint, I'm not going to go into the details. The details of this was published in an HPCA paper earlier this year. Now, again, given the interest in perhaps some of the folks here, I'm going to sort of highlight what changes it meant for the software. So if you were to execute 2 kernels with communication in between, this is what it would require you. You actually do the computation, you send the data to the host, you perform the communication, and then you send the data back, and then you launch the next kernel here and execute. So what we're proposing here is that, well, instead of doing this sort of fashion, you do all these sort of pre-processing here, and you combine this into a single kernel, where you offload the kernel as well as the actual communication itself, and then the kernel, the follow-on kernel as well, to the DPU, such that you don't have to go through the host. Right. So again, it allows you to have this sort of direct communication between the two. And again, this has to obviously be supported both by the hardware as well as the software. So again, I don't think this is a simple problem to solve. Again, it needs both sort of the support from both the hardware and the software, but also faces significant constraint, both from a hardware packaging perspective, as well as from a software perspective. Again, you want to make sure you have minimal impact on the actual interface itself, but obviously want to make it programmable as well. So when we did this, we were sort of trying to use the NVIDIA GPU model in terms of collective communication as sort of a starting point where you're sort of offloading the kernel to the processing core as well. Now, let me switch gears and talk a little bit about, given the domain-specific architectures, what does it mean for memory management? So there's two work that we've done the past couple of years where we looked at memory management for both a domain-specific architecture as well as domain-specific memory or PIM architecture. So one of the works we did, this was several years ago, where we actually proposed MMU for a NPU type of an architecture. Now, if you read through the papers, all the key observations is not surprising to anyone that has studied memory management in any sort of way. But I think the key aspect here is that it hasn't been done for an NPU type of an architecture. And obviously, you want to sort of exploit the various different characteristics of the workloads that we were targeting back then. So again, just sort of plopping down a whole bunch of page table walkers was not going to be the most cost-efficient solution. So it goes through various different ways of how we can sort of keep better track of outstanding requests without having to put a whole bunch of page table walkers. So again, the key insight here is the fact that, again, if you have different architectures, the current assumption is that, well, you don't need a memory management unit. And again, in some cases, you probably don't. But in other cases, you should start thinking about introducing memory management units. Now, the second aspect is this work that was done in collaboration with other folks, including Hynix here, is how memory is managed in the PIM architecture. So again, PIM is great. It allows you to put compute near the memory. But the key thing is the memory itself is very limited. You're talking about a few gigabytes at most, right? If you're trying to run any sort of a reasonable workload, you're going to need a lot more memory capacity than that, which means you can't get away with a single PIM device, right? So the fact is, well, how do you integrate all that? Well, you have to scale out. So here I'm going to take a picture out of what Hynix presented a few years ago, where they actually scale out the PIM system in a hierarchical manner. Right, you have individual ALUs in banks across various different chips and across various different nodes to be able to provide the amount of memory capacity needed, as well as obviously the memory bandwidth and the compute throughput as well. Now, having said that, I think the key observation or the key interesting aspect that we've looked at for PIM here is how do we manage the memory itself? So again, the key difference of this particular work was that we were looking at LLM inference in terms of long context. And again, the challenge here is that you have diverse set of input context lines. And a lot of prior work, we're assuming you're running in one particular load, you have a fixed amount of memory you're going to allocate, boom, you're done. But obviously, that's not going to be the case, right? Again, dynamic memory management is something you learn in your introductory computer architecture classes. But what we're trying to sort of identify here is that this also needs to be done for a PIM sort of an architecture. Now, the interesting aspect here is that once we sort of fix all the memory management aspect, the interesting thing that was learned from this particular work is that the I/O all of a sudden becomes a bottleneck, right? It's not the internal DRAM where it's the compute, but it's the I/O that actually becomes the bottleneck as well. So those are some of the things that you need to consider when you especially have good memory management. Now, again, I've talked a lot about technology, and I thought I would wrap up this talk with talking about some of the technologies I think maybe will be considered, you might see in the very near future that will definitely affect how we think about memory or memory management. Again, you've talked about sort of, I would say, general purpose memory. You have your LPDDR, GDDR, HBM, and then you have PIM sort of memory on the extreme case, the various aspects that I've talked about before. But now you have sort of something interesting in the middle where people are talking about this notion of a customized HBM. Again, it was sort of hard to find any sort of picture related to this, so this is some of the pics that I could grab from Marvell's website here. But the current HBMs have a memory stacked on top of a logic layer. The logic layer was, for the most part, handled with memory processing technology, which means it did not give you the opportunity to put a whole lot of transistors. Starting with HBM4, they're actually moving the logic layer technology to a logic technology, which means you can put a whole bunch of other logics on top of that. And the key difference is that the IOs are no longer restricted to DDR, right? So again, the tiny circle here on the bottom sort of highlights what could change with this new customized HBM. But the other thing is there's two other things that needs to be noted here is now you have a whole bunch of area, silicon area, to put compute if you wanted to. But if you look at now all the other aspects of the HBM chip itself, it allows you to have more IOs added to the memory, which means you could connect up the HBM to other chips, whatever that might be. Again, that could be more HBMs hanging in a sort of a daisy chain, or it could be sort of other memory technologies added on top. So again, the key thing here is that this is perhaps, again, this is not a far-fetched technology. This is something that you might see in the very near future, and it's just something that we as a community should be worrying about in terms of how we treat this, both from a memory hierarchy perspective and memory management perspective as well. The second part here is sort of, I think everyone has sort of seen this, and I guess I'm sort of biased because I'm starting my sabbatical at TensorTorrent, and they're really big on chiplets. So I'm just going to talk a little bit about chiplets. Again, I think all of you have heard of this notion of chiplets. It allows you to integrate various different aspects, and it makes a whole lot of sense from a business technology perspective. But again, at the end of the day, it's sort of all about how do you manage all that resources, the components. How do you integrate them together, and how is the entire system viewed? Now, it's going to be pretty clear whatever systems you build out of a chiplet, it's going to be heterogeneous, right? You're not going to have uniform die chiplets across. You're going to have different types of chiplets. You're going to have memory chiplets. You're going to have different memory technologies. And on top of that, my favorite part is obviously the network. How are you going to connect all these together? And how is that actually viewed by the programmer or from the system's perspective? So again, I think those are some of the new technologies I think people will have to worry about in the very near future. So let me try to summarize what I've talked about. Again, this summary is just a list of various different questions that I thought people should be thinking about. I think the basis of computer architecture has been Moore's Law, which is all about technology. Now, technology has and will continue to evolve. I don't think that will stop evolving. And memory technology will continue to evolve in one way or another. Again, whether it's sort of a CXL memory or a PIM sort of a structure, or it's different type of 3D stacking. The question is, well, how is that going to be integrated, or how is that going to be integrated to the compute part? Again, wherever that compute might lie. And obviously the question will be, how do you manage the memory? I think for many, at least for the students, some people often look for just new problems. Sometimes it's the same problem in a different setting, and I don't think that's really a bad thing. because the same solutions that apply to a previous problem might not be applicable. So those are some of the things to think about. And I think one can argue that memory, both in terms of capacity and bandwidth, will continue to be a bottleneck. So again, is the commodity way of DRAM. I think for the past 20, 30 years, DRAM has been viewed as sort of a commodity. Will that still be the case? Again, there's obviously the benefits of economy and so forth, but will memory itself become domain specific? Now again, I started off this talk with a eulogy for a memory vendor company, but processing in memory or near data processing or in different forms of compute near memory remains, I think, an attractive alternative. How it gets integrated, how it gets adopted by the community or the industry, obviously still remains to be seen, but obviously does provide significant benefits. Again, I haven't talked about all the benefits, but in terms of bandwidth, not only the memory bandwidth, but in terms of power savings and so forth. So with that, thank you, and I would be glad to take any questions.
So when you mentioned your work, Janus, so the problem was that there's a lot of shared data between MPU's memory space and PIM's memory space. But what if we consider batched inference? So if we consider batched inference, then often case most linear layers become matrix multiplication. So the only matrix vector multiplication will be attention head. So in those cases, I think only KV cache need to be stored in PIM's memory space. So it doesn't seem to have a lot of shared data between them. So is it like out of scope for Janus?
No, I think that's a very valid question. But I think you're giving me one example. I think there's a lot more example where the balance between the NPU usage and the PIM usage will vary, right? Some work will be dominated by the NPU usage. Some might be dominated by the memory PIM usage, and some might be sort of mixed half and half, right? So I think it's really important that you sort of be able to adapt to the different types of workloads, right? And again, even if you don't have any sharing, you still have the added benefit of memory capacity. So it gives you the benefit of being able to run bigger models as well. So I think there's definitely benefits to that. Again, what is the right balance? Again, one thing I didn't talk about is there's a balance in terms of how much compute you put in the PIM, right? You could put in one compute unit for one memory bank, or you could put in one for two memory banks, right? And obviously there's various different trade-offs along those lines as well. So again, I think that's a very valid question. It will depend upon the workloads. But again, I think that's why I would argue you need to unify the PIM with the main memory as well.
Thanks for the great talk. One of the things I was thinking of as you walk through that is the question of distribution in the network that you talked about, so the PIMs can communicate, and the different application domains where someone might use this. And one application domain that's probably dear to quite a few people in this room is something like garbage collection, where you're doing a graph walk, graph traversal, you're doing pointer chasing, and you don't have that locality you might get with a matrix multiply or something like that, where you can just do a transpose and put it into the different PIM banks or whatever, memory banks or whatever it is. Instead, you've got to follow pointers, so you've got this locality thing. So that seems like a very different application. Well, it seems natural in the sense that it's memory bound because you're doing a graph traversal, but it seems difficult in the sense that you've got this this problem with the distribution of the memory. So I just wondered if you had any super high level thoughts on the application domains that are going to be working with this and those that aren't, with respect to things like locality.
That's actually a great question, and I asked a similar question to my students, so I wasn't able to get a great answer, but I'll try to provide you with my thoughts. The work that we did, we sort of cheated in the sense that the communication was very structured, regular, right? So it was sort of like a collective, all reduced sort of operation where you know exactly what's going on. So what we meant was we were able to design the network to accommodate that. It was not a general purpose network. Now, if you have something very random, you would actually have to provide a network that supports our random accesses. And I would argue that might be too costly to supply in the PIM architectures. But hierarchy, I think, is our best friend here. You don't need at every level of interconnect to provide the full connectivity. I think if you provide us, let's say, a chip-to-chip connectivity through, let's say, a buffer chip. Again, it's maybe not as provides you as much locality if you had sort of bank-to-bank, but I think it's a nice compromise. So I think these type of workloads are exactly why I think you need some amount of communication within them. But having said that, the biggest challenge I would argue is that now the host does not see you as a memory because now the latency, everything is non-deterministic. Again, the work that we did, we assumed PIM was working in sort of a deterministic manner because the communication itself was deterministic. But if you have a random access, I think it's an interesting thing to explore. It definitely would improve the benefit of PIM itself, but then you also have to worry about this. Do you want to have a full-blown general purpose network or not, or something in between? How is the host going to be able to manage that, given that it's going to be random access as well?
Thanks again for a very interesting talk. There's something I was wondering when you were talking about the distinction between seeing PIM as an accelerator or memory. Something that's come up in workloads I've seen in the last few years has been an innovation in terms of the storage formats for floating point in HBM. So things like the MSFP block formats where you have a shared exponent between a bunch of mantisses that are then stored. And that can be challenging to program with GPUs because you have to load the data and convert it from that block format to what the GPU is wanting to be processing and figure out how to do that in the maybe the different block sizes that the tensor core is designed to handle. I was wondering how you'd see that kind of data type conversion fitting in here, whether some kind of on-the-fly conversion that would let people innovate in the storage formats would be something that current PIM systems support, or maybe an interesting direction in the future.
I think it's a very interesting question. I don't have a good answer, but I think some of the things that you can think about. For example, one of the Hynix PIM, I believe, just supports a single format, right? So obviously that does not give you the flexibility. If you did something with something similar with an ISMM type of PIN, you could do whatever you want because again, you have a general purpose core. It could do even floating point operations and so forth, but it would emulate everything effectively. So the performance would obviously drop significantly. To be honest, I think it would sort of have to come down to sort of a balance of in terms of memory bandwidth, memory capacity, compute in terms of what needs to be done, as well as the communication over it. So again, what is that right balance? And does that make sense to introduce that to save on the capacity versus the compute overhead? So again, I think it comes down to how you're going to design the entire system. So again, whether you view it as an accelerator memory, it's only one part of the system. It's right. I think you have to look at the system as a whole to be able to come up with a great answer for your question.
Any final questions? Okay, well, let's thank John Kim again for getting the And I'm pleased now to introduce the first of the research papers at ISMM this year. This is continuing the topic of processing and memory. And the speaker is going to be Ryu Morimoto talking about Gray and Young, a generational garbage collection for processing in memory.
Good morning. I'm Ryu Morimoto from the University of Tokyo in Japan. Today I'm going to present our work titled Gray Yin Yang, a generational garbage collection for processing memory. As mentioned in the keynote by Professor Kim, processing memory referred PIM is attracting attention. A key feature of this approach is that computation is performed where the data resides. Please take a look at this figure. In a conventional architecture, the CPU and memory are connected through a memory bus. To perform computation, data is repeatedly transferred between the CPU and memory over the bus. In memory-intensive application, a massive data is transferred, which becomes a performance bottleneck. In contrast, the PIM approach places a processor near the memory, and the processors process data there. This approach is expected to solve the bottleneck caused by the massive data transfer between the CPU and the memory. UPMM PIM was a publicly available PIM device. In a UPMM PIM system, computations are performed on UPMM PIM-enabled memory. The structure of this memory is shown here. DRAM processing unit, or DPUs, are in the DRAM chips. And each DPU has its own instruction RAM for storing the binary for DPU and scratchpad memory. DPUs access DRAM through DMA. In this research, we developed an efficient garbage collection for virtual machines running in a single DPU. There are two challenges. The first challenge is that fine-grained DRAM accesses are slow. Therefore, in garbage collection, small DRAM accesses such as pointer-sized loads or stores should be minimized. The DPU accesses scratchpad memory in one cycle. However, it accesses DRAM through DMA. This graph shows the throughput of DMA. The higher the better. As you can see, throughput with small DMA size is very low. According to an experimentation done by another group, a single DMA transfer spends at least 70 cycles. With large DMA sizes, overhead of DMA transfer is alleviated. The second challenge is that the instruction RAM is very small, only 24 kilobytes. Because of this, we must reduce the binary size so that the binary fits within the instruction RAM. Here are our contributions in this work. We have developed a generational garbage collection for DPUs. This garbage collection is designed to reduce DRAM accesses through DMA in minor collections. Moreover, we designed the garbage collection to keep the binary size small. This is an overview of our garbage collection designed for DPUs. We place the young generation in the scratchpad memory and the old generation in DRAM. The class table is also placed in DRAM. Minor collection runs in parallel, and we apply two techniques to reduce DRAM accesses. Major collection is a more compact garbage collection. Currently, it is a single-threaded. Parallelization is left as future work. In the rest of the talk, I will mainly focus on these techniques. Okay. So let's look at how DRAM accesses occur during a minor collection in an ordinary algorithm. Here, we focus on this orange object. First, the object is copied to the old generation. This W mark indicates a write access. Because this copy is done with a single DMA, I put a single W mark here. Next, we access the class table to know which fields in the object are pointers. So I put our arrow mark for these. In this example, we can see that 2 fields have pointers. Then we need these fields to traverse their child object, so I put 2 arrow marks for these. Later, each child object is also moved to old generation, and here we assume they have been moved as shown. Finally, we update the pointer field of this orange object to point to the new location of the child object. So I put 2 W marks. As you can see, this process involves many reads and writes to DRAM. This is because the object is accessed for traversal and pointer updates after it is copied to DRAM. In other words, the object is copied while it is gray in trickle abstraction. To reduce these DRAM accesses, we propose to keep objects in the young space while they are gray. In this method, reading and updating pointers are performed on the scratchpad memory, not on DRAM. After all pointers have been updated, the object is moved to DRAM. The object is moved to DRAM in a single DMA operation. I will explain details of this algorithm with this example. A is pointed to from the root set, so A must eventually be moved to the old space. Unlike the ordinary algorithm, we do not immediately copy A to the old space. Instead, we reserve space to which A will be copied and install forwarding pointer to A. Then we scan A in the young space for its children. In this scan, we find C and B. We move them to the old space in the depth first order. For C, we reserve its destination and then scan it. Now we find a pointer to A, which we have already visited. Since A has a forwarding pointer to its destination, we can update the pointer in C. Once all the pointers in C have been updated, we copy C to the old space with a single DMA. We move B to the we move B to the old space in the same way. Now all the children of A has been moved. We updated pointers A in the young space and copied to the old space. First, we update pointers A in the young space. Then finally, we copy A to the old space. Next, we focus on these accesses to the class table in minor correction. For each live object, the corrector reads the object layout information, or OLI, from the class table, which is stored in DRAM. Because this access happens once for every live object, it results in a large number of DRAM accesses. To reduce these accesses, we take advantage of the characteristic of the virtual machines assumed by our garbage collection. Our garbage collection is designed for the Java framework for UPM PIM. In this framework, Java methods can be offloaded to DPUs. For each method that can be offloaded, the framework prepares a dedicated binary for the DPU. We refer to such method as kernel method. An important characteristic of the UPM system is that when a new binary starts execution on the DPU, the contents of the scratchpad memory are cleared. In contrast, DRAM contents are preserved across multiple binary execution. Therefore, we move all live objects to the old space and empty the young space when a kernel methods are complete. So, Our second proposal is to cache object layout information in scratchpad memory. To take advantage of the property of the system, we make an optimized image of cache for each DPU binary. As we see in the previous page, we empty young space when a kernel method is complete. In this figure, when insert method is completed, young space becomes empty. And then the next kernel method starts with an empty young space. As a result, all objects subject to minor correction were created with the currently running kernel method. Based on this observation, we prepare optimize cache image of OLIs for each method in advance. When the method starts execution, the corresponding OLI cache image is loaded into the scratchpad memory. Finally, to address the limited size of instruction RAM, we propose separating the major correction binary. In this approach, as shown here, only the minor correction is linked to the computation kernel that runs on the DPU. The major correction code is excluded from the computation kernel. When a major correction is needed, a separate binary containing only the major correction is executed on the DPU. With this separation, we reduce the size of the computation kernel by approximately 6.9 kilobyte. This design also has an important advantage. Since the major correction is isolated in its own binary, we can allow its code size to grow in the future. For example, if we improve its performance or implement more complex logic. To evaluate the performance of our proposed garbage collection, we developed a micro benchmark. This benchmark repeatedly creates a binary tree by inserting elements. Once the number of elements in the tree reaches a certain threshold, denoted as alpha, the tree is replaced with an empty one. As alpha increases, more objects survive in the young generation and get promoted to the old generation in minor correction. This graph shows the total time spent on minor correction. The lower the better. For each value of alpha, we applied our proposed techniques, graying young and OLI caching. Across all alpha values, we observe consistent speed up when applying these techniques. At alpha equal 100, applying the graying young techniques alone resulted in 31.5% speed up. Adding OLI caching further improved the performance, reaching a 46.2% reduction in garbage collection time. To understand the cause of this improvement, we analyzed DRAM accesses in minor correction. The left graph shows the number of DRAM accesses, and the right graph shows the total number of bytes transferred. The lower the better. In both graphs, we can see that our proposed techniques significantly reduce DRAM accesses during minor correction. At alpha equal 100, graying young alone reduced the number of DRAM accesses by 36.3%. With class table caching also applied, the reduction reaches 85.9%. These reductions contribute to the improvement in minor correction time that we saw earlier. This chart shows the scalability of our parallelized minor correction. The lower the better. As we increase the number of threads, the garbage collection becomes faster. We observe the highest throughput when using 11 threads. However, for small alpha values such as 7 and 15, the throughput is saturated at fewer threads. This is because when alpha is small, there are fewer objects promoted from young to old generation, which means less work that can be shared across threads. Let me briefly let me briefly introduce related works. Generational garbage collection that places the young generation in the scratchpad memory has been studied in prior work. This work mainly proposed a pre-tunneling algorithm. Unlike our work, they also place long-lived frequent accessed objects, so-called hot matcher object, in the scratchpad memory. Another line of work focuses on identifying pointer field during object scanning. While our GC, our garbage collection, simply reads object length information from the class table, there exist several prior studies that propose optimized techniques for object scanning. This is summary. Thank you.
We have time for a few questions.
How difficult would it be to do a benchmark, a real benchmark to run on this?
Okay. So in my work, benchmark is only one seat, and the difficulty of making benchmark is that first one is yes, instruction RAM is very limited size, and second that benchmark for this DPU UPM PIM is not there are no suitable benchmark for DPU. So yes, this 2.2 yes, that is difficulty.
The question is, I know you look at the class information to know the object layout to find the pointers, but this is only one way to find the pointer. There are also alternatives, such as one example is that you put a small bitmap in the object, right in the object header, so that you no longer need to look at the class information. Have you considered this method, and what do you think the impact of this would be?
Yes, that is one way of identifying pointer. And so if object the header contains bitmaps, so if bitmap is 8 bytes, each object increases the size of object header, so the heap is more more and more minor collection, garbage collection is more time triggered because the heap will be soon full. So yes, but yes, as I mentioned in related work, that is one way, and we don't apply the optimization for identifying pointer.
Maybe one last question.
So thank you for the question. I have a question about the latency factor. So as I understood, I guess you measured your throughput only for a single kernel execution, and I guess the minor garbage collection between across kernel executions may enable latency. So do you have any insights about that?
Thank you for question. So yes, if the as our feature works, if the latency sensitive application, like incremental ZC garbage collection is one of the way to reduce latency. But now our garbage collection is stop the word garbage collection, so latency is yes, if the GC is occurred, the latency is not latency is high. So yes.
Great. Well, let's thank the speaker again. I will have a coffee break next and continue with the next session at 10:40.
Okay, so it's like this. No, it's fine. It's fine. Don't worry.
You should do a shout out at the start with the sessions. Have you got slides? Have you got a slide?
Oh, excuse me, sir.
Why don't you make a slide? Maybe just have a look. Just move it up. Yeah. Okay, so make a big slide. Yeah, that's fine.
If I read all of these, then maybe not.
You want to do it when the most number of people here, so it should have been started.
I mean, let's see. Maybe there's a.
There are no submissions so far. But I'm just about to put an abstract in for you.
Well, what you could do is if you have a slide that you just want to put up, we could do that during the break while people are coming back from the lunch break. Okay. So you could just take the laptop, put it up
Before the session.
before the session begins. So press it up. And just yeah, just feel free to
If they made it. Okay. So welcome all to the second great session of ISMM today. Our first talk is by several co-authors from ANU, Google Relational AI, and Julia Hub. Lin will be giving the talk, and it's about reconsidering garbage collection in Julia, a practitioner report.
Hello. Today I will give this talk and we will share our past few years' experience working on garbage collection in Julia. So this talk is not about performance, it's about software engineering on garbage collection in Julia. I will talk about the challenges we faced, the decisions we made, and the lessons we learned along the way. So this is a collaboration between the MMTK team, Relational AI, and Julia Hub. Relational AI is the sponsor of this work. They are one of the largest users of Julia in production. They build their core systems all in Julia, like the compilers, database engines, web services. So Julia is mostly known for its use in the field of scientific computation. So you can see the workload from relational AI is quite different. So this exactly motivates this work. So we need the need to rethink about garbage collection of Julia in the context of large-scale and memory-intensive systems. So this brings us to our first motivation. Julia's current garbage collection, which is a sticky mark-based collector, it performs well in certain domains, but it's suboptimal for memory-intensive workloads, particularly in terms of memory fragmentation. So what would be a solution to this? At first glance, it will be seems obvious. We just replace this GC with a better GC. But the question comes, what do we exactly mean by a better GC? So we see like some GCs are optimized for latency or pause time, throughput, or fragmentation, and some GCs are more concerned about the complexity of the GC itself or its interoperability with native code. So this brings us to our second motivation of this work. So we see there's no silver bullet GC. So every GC is made with different trade-offs, and they target with different priorities. So we don't want to replace the current GC with another GC. Instead, we want to introduce an interface that enables Julia to support a wider range of GC algorithms depending on the needs of users' workload. So the goal for this work is we want to introduce a GC interface. We want to be able to run multiple GC implementations with Julia. And we want to enable more advanced support for Julia. For example, the copying GC, not that advanced. So before we dive into our experience, I'll give a little bit of background. So first, Julia is high-performance, dynamically typed languages. It's designed to be as easy to use as other dynamic typed languages like Python, but while being able to deliver good performance like statically compiled languages. There's a bunch of interesting features about Julia. The only thing I want to mention here is its seamless integration with C. So calling C function from Julia is easy and efficient. It's so easy, so it becomes a pattern that the Julia users, they just wrap and reuse native libraries in their Julia program. So this is absolutely good for programmers, but it causes challenges for GC developers. So Julia's current GC, it implements a sticky mark bits collector. It's strictly non-moving. It has a generational behavior. In terms of allocation, use a free list allocator. For small object, this is also known as the pool allocator in Julia. For large object, it uses malloc. And for permanent object, use malloc or mmap. Also, Julia may have object in the system image, in the pre-compiled system image. So Julia uses post-red barrier to capture updates to mature object. This is common for generational GCs. And Julia GC is also precise. They use shadow stack to record all the roots, and the tracing starts from those roots. So MMTK is an open source framework for building garbage collection. It includes a various of different garbage collectors, also known as GC plans. So this talk is not about MMTK. We use MMTK mostly for two reasons. One is we're familiar with it, and it's convenient for us. And the second is this framework has a well-defined GC interface. It has been ported to different languages. So use this for us to experiment the GC interface for Julia is a good choice. So in the rest of the talk, I'll talk about two parts. One is about how we integrated non-moving GCs with Julia. And the second part is how do we support a moving GC in Julia. So for non-moving GCs, we selected a list of GCs and integrate them in the order of increasing complexity. So in this way, we only need to focus one piece at a time rather than getting overwhelmed by the complexity. So this approach turned out to be very effective. So we started with a very simple GC called NoGC. So it just only does allocation and no reclamation. So this allows us to explore the allocation interface for Julia. Once this is done, we worked on the first real real alternative GC for Julia. That's Emix. Emix is mark region collector with optional opportunistic copying. So at this stage, we disable copying, still to make things simple and manageable. So this, in this part, we use Julia's own GC as a reference. So we implemented the root enumeration and object scanning for MTK GCs. And we also found that a large chunk of Julia's existing GC utilities can be reused, like the save points, weak references that finalizes. And once this is done, we move to a similar collector that's very similar to Julia's sticky mark sweep. We use a sticky immix, we still use the non-moving variant here. So in this part, allows us to understand how red barrier works with Julia. So a general experience for this part of work is it was smooth. The reason is the alternative GCs is more or less like its existing GCs. So the runtime and the language design already have good support for this style of GCs. We also found some quirks along the way. For example, like buffer object, this is a special kind of object. They don't have any pointer information, so they cannot be scanned by the GC standalone. They have to be scanned along with the object that owns those buffers. I won't talk through about its topics. So if you are interested, you're welcome to take a look at the paper. This is a roadmap for what we have done. So you can see that the prototype for all those non-moving GCs is mostly done in 2023. And in the last year, we upstreamed the GC interface and we upstreamed the non-moving immix. And we're also in the process of upstreaming the non-moving sticky immix. So all this work is actively making its way to Julia's GC ecosystem. So let's talk about moving GCs. So as we said, that non-moving GC has a fundamental issue that will cause fragmentation in the long-running workloads. You saw that we have done the non-moving GC mostly in 2023, now it's 2025. That's roughly how long it took us to move object in Julia. So why is this so hard? The reason is simple. There's a deep assumption about non-moving in the language runtime, in the compiler, in the language semantic, and also even in the user patterns. So let's look at one simple example. This is a snippet of Julia runtime code. There's nothing too special about this code. You can see this everywhere in Julia runtime. This pattern here is very common. So let's look at this. So from this code, we have a root pointer pointing to it's from outside the heap, pointing to a heap object. So this is a root. By definition, it's a root. And later we'll have another root. So but what you can see is for the first root, there's a JL GC push. So that identifies this root and put it to the shadow stack. So we would expect that for the second root, we should have another push as well. But the thing is, for Julia, they don't do that. Why? So if we look at this code again, there's one piece of key information that's missing. So there's a pointer between the first object and second object. So in this case, the first object, that EXPR object, is kept alive by a root. So that means the second object will always be kept alive. So we call the first kind of root a dominant root because the object it points to appear as a dominant node in the object graph. And similarly, we'll call the second kind of root a dominated root. So if we only look at the object liveness, the dominated root seems unimportant because those objects are always kept alive. So under the assumption of a non-moving GC, Julia assumes that keeping an object alive is sufficient. So in that case, Julia does an optimization. So they omit the report of dominated roots. So that's why we don't see Julia push the second root to the shadow stack. But obviously, this only works if objects don't move. So what happens when we have a moving GC? The garbage collector comes, see the first object. It knows this is a root and possibly being used in the native code. So the garbage collector can keep this object in place. There's no problem. But when we see the next object, there's no information for GC to know is there anything special about this object. So GC thinks, okay, I can move it. So it moves the object. Then what happens is this, what should be a root pointer now become dangling. So we found this core assumption in Julia. That is, if an object is kept alive, then they assume all the pointers and all the references to this pointer to the object will remain valid. We observed that this shows up in several ways in Julia's runtime. For example, the example I just explained, they could use this information to skip identifying certain roots. And also inside their GC implementation, they can use this information to skip tracing certain routes or skip tracing certain fields, as long as they know the object that is referenced by the route or referenced by this field is kept alive. Also, this shows up in their FFI. So explicitly, Julia says that the users need to keep object alive. Then they can use it. They can store it in their native program with no issue. So the middle two things is about GC implementation, and it's relatively easy to fix. So I'll talk about the other two. So initially, we tried an idea, we call it transitive pinning. The idea is if we transitively ping an object, then the object will be kept alive, and all the reachable object will be kept alive and also be pinged in place. So in this way, we can make the GC to satisfy their assumption. That is, if an object is reachable, it will be kept in place. So we have an efficient implementation for this. We just do an initial tracing that keeps those transitively pinged object in place. Then we do the normal tracing that try to move the remaining object. We had this working, but the problem, it pings most object, as you could imagine. So clearly this is not ideal, but this is a still useful mechanism for FFI. So when you pass a pointer to FFI, to your native code, you can use transitive pinning that give you a conservative and safe way to use this object. So instead, we took a different approach. We tried to identify the missing routes based on their location. So we found that there are a few places those kind of missing routes could appear. The first is obvious on the stack and in the registers. So we use conservative stack scanning. So in our conservative stack scanning, it's a bit different. When we find any potential references, we don't use them as routes. We just use them to ping those objects. So in that case, the GC is still precise. And the second place that this kind of routes could appear is in GDIT code. But fortunately, there are only 3 places in the compiler that they emit pointers. So for simplicity, we just ping those objects that gets emitted into the code. The third location is the runtime native heap and the global memory. So the runtime is written in C and C++. So they may have data structures that in the C++ heap that reference Julia objects. So we identify in total around 11 runtime types that may reference GC object, but they're not really traced by the GC. So although when we identify those places, we also ping those objects. So the last location is the FFI. We realized that the current FFI is insufficient. It just simply don't give GC enough information to do copying. So we propose a new FFI, and the key to the new FFI is that the user will have to notify GC before their use of the pointers, and they will have to keep GC notified during their use of the heap pointers. So for this part of work, we have an Emacs that working with transitive pinning in 2023. And in this build, few objects can move. And roughly 1 year later, we have Emacs that without transitive pinning. And in this build, most objects can be moved by the GC. And just in last month, we made a proposal for the Julia community about the FFI. So as a summary, we introduced GC interface for Julia. Both MMTK GCs and Julia's existing GC works well under this interface. We found it relatively easy to introduce new GCs under Julia's current constraints. That is non-moving, non-generational, or generational with object read barriers. We also found it possible to use moving GCs with Julia, but the GC has to provide efficient pinning support, and we're still improving moving GC with Julia. That's all for this talk. Thank you.
Thank you for a great talk. It's great to have practitioners come and explain what they're doing. So, did you say anything about concurrency, or is Julia concurrent? Is the garbage collection concurrent?
it's not concurrent, but it has a sweeping phase that can be done concurrently. Basically, just tell the operating system with M device to reclaim those memory. That's the only concurrent part. Otherwise, it's not concurrent.
Okay. Any questions? Yeah. There is a remote audience, so please say your name and the affiliation.
Hello, Jeremy Singer, Glasgow University. Thank you for your talk. This is a question about social engineering, I think. How easy was it to convince the Julia community to accept your changes and to get them upstreamed? I mean, were you viewed with suspicion or welcomed with open arms? Thank you.
This is an interesting question. So yes, we have seen some resistance, like people really like their current GC. And actually it works well for certain domains, as I have said. But there are also needs that other people want a different GC that works better for their workload. So that's the reason we not want to replace what they have, we give them something more. So I think in that case, we see much less resistance.
Yeah, we have time for one more question.
Martin Maas, Google DeepMind. Really enjoyed the talk. Do you see ways how the work on doing this for Julia could make it easier to adopt these GCs in other languages? Like, is there things that can carry over directly or indirectly?
I think there are two parts. One is, as you see, we use the framework MMTK. And when we put this framework to more languages, we're more confident in its own interface. That's one thing. And the second is a lot of things we learned in this experience is there's assumption in there that maybe really no one really figure them out what the assumption is. The assumption is there, but no one realized that. And we learned it in hard way throughout a lot of debugging. And then we realized, oh, they just don't tell us the roots. That's quite a surprising thing, actually.
Okay, thank you very much. Our next talk is by Kunshan Wang, together with Steve Blackburn and Peter Zhu and Matthew Valentine from ANU and Google and Shopify. And Kunshan will give the talk.
Yes. Yes. Thank you. So this research is a collaboration between the ANU and Shopify, and CRuby is the Ruby implementation that powers this company. And let's start. And this talk is dedicated to Chris Seaton. He was our collaborator at Shopify, and he started this project, but unfortunately, he passed away 2 years ago. And this talk is a practitioner report. We will introduce our experience of integrating another GC implementation into CRuby, and in this case, this is MMTK. And I can assure you, this is full of challenge. And let's talk about CRuby. Mr. Matsumoto Yukihiro created the Ruby programming language in 1995, and it started with a pretty standard mark sweep GC algorithm. But there's one peculiar aspect of this algorithm, is that all objects are 40 bytes in size. Strange. You may ask, one size doesn't fit all. What about big strings, and what about big arrays? And CRuby's answer is just call malloc. Yes, the malloc in C standard library. You see, when an object needs more memory than that, it will allocate its payload using malloc and let the GC object hold raw pointer to those buffers. And some GC objects even hold multiple such buffers. But the CRuby's GC is constantly evolving. In version 2.1, it introduced generational GC. Because it's still non-moving, it uses in-header sticky mark bit to denote those objects. And in version 2.7, introduced compacting GC. This allows objects to be moved around to mitigate fragmentation. And in version 3.2, it introduced variable width allocation. Now objects come in multiple size classes, and slightly larger objects can now fit into the GC heap in larger size classes.
But despite continued development effort, the CRuby GC is still not 100% satisfactory. The compaction is still costly, so it's triggered manually. The objects are still limited to 640 bytes, and GC is still single-threaded. Then what can we do? Of course, we can continue to improve CRuby's GC, and we can also do something radical, such as we rewrite the GC from scratch, or we replace it with an existing high-performance GC. But we don't think replacing the GC is a good idea. Instead, the more rational approach is to extract the interface between the VM and the GC so that CRuby can adopt other GCs if they want, including MMTK and anything else. And let's talk about MMTK. MMTK stands for Memory Management Toolkit, and is a framework for garbage collection. It comes with lots of garbage collection algorithms, and it supports parallel GC and comes with performance analysis tool. But this talk is not about MMTK, it's how to get CRuby work with another GC. If you are interested, please, you are welcome to visit our website. So now we have CRuby and we have MMTK, and shall we just plug MMTK into CRuby and expect them to work directly? Not yet. Note that this project started in year 2020, at which time CRuby still didn't have a modular GC API. So before integrating MMTK, it's our job to identify the GC interface in CRuby, and we do this in multiple steps. Step 1, we support no GC that we allocate but don't collect. And in step 2, we support non-copying GC, and step 3, we support copying GC, and in step 4, we support generational GC. And in each of the steps, we identify part of the VM GC interface, and in step 3 and 4 specifically, we use IMIX and sticky IMIX GC algorithm because CRuby needs object pinning. And we have faced many challenges, but limited by time, this talk we are going to omit some of the challenges and only go deep on some of the selected challenges. And if you need more information, you can always read the paper. Also, let's start with part 1, no GC and the allocation interface. So do you see the function over there? CRuby called that function to allocate heap objects. So just wire that function to MMTK and we are almost done. And then we just need to do lots and lots of trivial work. And luckily, I don't have to do any of them. So thank you, Angus Atkinson, a student at ANU who initially worked on this project. With his work, we were able to run Rails on CRuby with MMTK with no GC. And then let's proceed to part 2, non-copying GC, where I took over this project. In this part, we dealt with stopping mutators for GC, stack scanning, and object scanning. But this part is kind of easy because we can mostly reuse CRuby's existing mechanism with minor additions. And it worked. CRuby can work with MMTK and a non-moving GC. Let's proceed to part 3. And this is copying GC and reference forwarding. So reference forwarding means when the GC moves an object, it needs to update its field so that it points to the new address of the object. Supporting reference forwarding itself easy. We just wire this function to those functions, and that's done. But the real challenge is that in CRuby, some fields cannot be updated. Yes, the object has fields, and some of the fields cannot be updated. You may ask why. To answer this question, we need to go to the history of CRuby's GC. CRuby started in 1995 with a non-moving mark sweep collector, but it didn't get moving GC until 2019. So during the 20 years in between, the Ruby community thrived. Third-party gems were developed, and CRuby runtime grew, but none of the legacy code written in this period were aware of moving GC. And because CRuby is written in C, the developers define object layout in terms of C structs. And to identify the reference types, the developer provide a so-called marking function to visit those reference fields. However, to support copying GC, moving GC, the old style marking function must be rewritten in a style that allows fields to be updated. This may mean that the developer may have to rewrite the marking function of all the legacy types. Or do they have to? But that's a lot of work, a lot of legacy code. So instead, the developers found a way to allow graceful transition. They allowed legacy objects and modern objects to coexist. So the legacy object on the left-hand side couldn't update their fields, so they pinned their children, so there's no need to update their fields. On the right-hand side, the modern object can update their fields, so their children can move freely. And in CRuby's mark compact garbage collector, it will start tracing, while during tracing, it identifies those unupdatable fields and pin their children. So during compaction, they can move all objects except the pin object. However, this simple idea doesn't work for MMTK's image collector because image is a scavenging GC. In simple terms, a scavenging GC copies object during tracing rather than after tracing. So during tracing, if the scavenging collector happens to visit the fields in the wrong order, for example, it visits this field first and move the object, and then it visits this field, but it finds the object is moved, but it cannot update this field. So to support scavenging GC, we must pin object before tracing starts. So in order to do this, we need to identify all objects that has unupdatable fields, and we call such objects potential pinning parents, or PPP for short. And when using image, during moving GC, because we identify the PPPs, we pin their children before we start tracing. You see, the tracing can update some of the objects, but not the pinned objects. And it worked. Now CRuby work with MMTK and the moving image collector. And we can proceed to part 4, generational GC. To support generational GC, it's important to identify the remembered set, that is the references from old to young objects. There are many ways to do this, and one way is to use the object remembering barrier. When assigning, we just remember the source object so that during the next nursery GC, it conservatively treat their fields as roots. Supporting write barrier is easy, just wire that function to that function is done, but the real challenge is that CRuby never applies write barrier to some of the objects. Those objects are called write barrier unprotected objects, or WB unprotected objects. But why does such object exist in the first place? Let's look at the history of CRuby again. Oh, you may say, I know the history, it's just legacy code again. Yeah, you are absolutely right. Legacy code is one part of the problem, and the other part is the poorly designed API. So you see, CRuby allowed the Ruby method to be defined in C, but it also has some legacy unsafe API that exposes raw pointers into the guts of objects and allows C code to assign to those fields without write barrier. Of course, there are safer alternatives, but some legacy code in the wild are still using those unsafe deprecated APIs, so the GC has to be aware of their presence. But fortunately, handling WB unprotected object is not that hard. We just treat them as if they have been updated before every GC, and this effectively keeps them in the remembered set until the next full heap GC. And we made it. We have gone through all the steps and faced most of the challenges. Now CRuby work with MMTK with sticky image. Oh, we should celebrate. Or should we? So when we measure the performance, it still sucks. So something is still not right. So in the end, we still need to face the remaining challenges. One is identifying the GC performance bottleneck, and the other is, wait for it, finalizers. So finally, let's go to the ultimate challenge, finalizer. A finalizer is an operation to be performed when an object is determined to be dead. It comes in many programming languages, and in CRuby, it's in the form of this obj-free function. And the real challenge, almost all objects in CRuby are subject to finalization. You say, that's madness. Finalization should be only be for a small proportion of all objects, but what's happening in CRuby? So do you remember that CRuby has an object size limit? CRuby's default GC is simply incapable of allocating any objects larger than 640 bytes. So if an object needs more memory than that, it uses malloc. Then the immediate question is, when do we free this malloc buffer? And the answer is, when this object dies, of course. You see, this is finalizer semantics. When object dies, do something. And in this case, it's freeing this buffer. So in CRuby, any objects that have associated malloc buffer are subject to finalization. So what objects? Well, almost all objects. Almost all types in CRuby have malloc buffers for one reason or another. So for this reason, the GC has to look at every single dead object just to see if they have associated malloc buffer and free them. And how bad is this? Well, we run the liquid benchmark with MMTK plus Emmix, where liquid is the templating engine. And we use an eBPF-based visualization tool to make a timeline to show what exactly is happening during a GC. So you see the GC can traverse the whole heap in a very short time, but spend much more time just calling the obj-free function on the dead objects. Okay, you can ignore that. So you may ask, this is single-threaded. What about you parallelize it, use the MMTK's worker threads? Well, if we parallelize it, it's even worse. So let's tidy up a bit. So just by calling that function in multiple threads, the performance degraded. This is quite counterintuitive. So why doesn't this finalization function scale? And the culprit is free. Yes, the free in C standard library. You should remember this I just called malloc. So seriously, we did a micro benchmark that freed 100 million small objects in multiple threads. We tried multiple malloc implementation that the more threads we have, the slower it becomes. And me-malloc is the only implementation that scales, but only accelerates to a factor of 4. And obj-free is all about calling free, so no wonder this thing doesn't scale. So what can we do about this? If we can't parallelize it, answer is we just get rid of it. So in other words, we refactor CRuby so that is to make it unnecessary to call free. So how do we do this? Remember, CRuby has a size limit, but MMTK doesn't. MMTK doesn't have a size limit. So instead of allocating those buffers in malloc, we just allocate this in GC heap and let the GC handle both the header object and the payload without using finalizer. And we inspected the distribution of dead objects, and we chose to refactor 3 types. They are string, array, and regular expression match data, so they don't use malloc. So instead of using malloc, they allocate their payloads in the GC, and they don't need finalizer anymore. And the result, very obvious. You see the finalization is become much smaller compared to transitive closure. But remember, this is Emmix. When we switch to sticky Emmix, the transitive closure bus becomes much faster, and finalization becomes a bottleneck again. So now we have already gone through all the challenges and steps, and what have we learned? History lesson, maybe. CRuby started with a non-moving, non-generational, blah, 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 but we are now aware of them. But I think it's a bit too late. Now we have to deal with potential pinning parents, right barrier unprotected object, and eliminate unnecessary finalizations. But what if CRuby started with a generational copying GC? If we engineer for a high-performance GC from the get-go, we won't need to deal with those challenges now. So let's read the overarching lesson aloud. Assumptions about GC, such as non-moving, non-generational, limited object size, etc., can bake bad design into the VM during early development, which make them more costly to fix in the future. And status quo, we are closely working with CRuby developers, and in fact, 2 of our authors, one thing there, are CRuby committers. And in version 3.4, CRuby finally got an official modular GC API and official MMTK binding. So let's end this talk by saying GC is important, and let's do it properly. Thank you.
Okay, so any questions? Yeah.
Thank you, I will. Hello, Jeremy Singer, University of Glasgow. Thanks for a really nice talk and a very nice layout of the different challenges. I wonder whether there's any potential for a kind of standardization of the GC interface. You know, whether it's kind of with POSIX or somebody like that, you know, a kind of very well-defined set of functionality and APIs that are needed so that new VM designers or people retrofitted things like yourself can work within a common framework. Is that something you've thought about?
Well, such things, I think it's not nice to have. Currently, we don't have this thing. But to find this thing, we need to, for example, investigate multiple GC algorithms to see what they need from the VM. And we need to investigate multiple VMs, and because each VM has their own characteristics and what they need from the GC. And we also need knowledge about the state-of-the-art VM implementation to know what's the best practice to so that we can eventually come up with a nice interface for that. And we are working on it.
Tim Harris from OpenAI. I really love the presentation here and all of these problems that came up, and then the next problem comes up and so on. And I was wondering if we had a slightly different GC, whether there'd be some more problems coming up on the list. So let's say we wanted to introduce a parallel collector or concurrent collector. Does that add any extra requirements beyond the one here?
Yes, definitely. Let's take a concurrent GC for example. If we need a concurrent GC, we'll make sure that the GC will synchronize with the mutators, and so that the right barriers are needed. So if a language that doesn't insert a right barrier properly in all the cases, it will be in trouble and probably need some refactoring. And similarly true for like other kind of GC.
Thanks. Really nice talk.
Yeah, thank you.
Yeah. Any more questions? Okay, so let's thank the speaker. And our next talk is actually remote, right? And I'll let the technical help bring it on screen. This is this talk is by Stefan Dolan from Jane Street. It's about lifetime dispersion and generational GC, and it's an intellectual abstract. Where is this there? It's right there. Ah, well, there he is.
Thank you. So this talk is collection is a good idea. It works pretty well. This idea of separating the heap, logically or physically, and having a separate nursery generation of the recently allocated objects, which is collected earlier and more frequently than the heap as a whole. And this turns out to improve system performance across a wide range of programs. So these are both fairly well established. And I'm not planning to contradict either of them. But what I plan to focus on here is the connection between the two properties. In fact, as we'll see, the generational hypothesis, as stated there, does not actually imply that generational garbage collection is a good idea. But I think both of these things are true, but that version of what the generational hypothesis is not really a very good explanation of why generational GC is so effective. So I'm going to give a couple of examples to explain what I mean here. Where we can compare the different versions of the hypothesis and whether generational GC actually works. So the first one of these is a very simple program that's just a single big queue. In this queue, most objects, this program inserts values into a queue, allocates new values, inserts them into a queue, and deallocates them from the far end of the queue and discards them. So every object lives exactly the same lifetime. They all live just long enough to traverse the queue. They all survive until they get to the end, until they are dequeued. and none of them die young. The next unreachable object is not likely to be young, and generational garbage collection does not apply. This is not a generational program. If you try to run generational garbage collector with this program, then you'll find that it just makes performance worse. The extra overhead of bookkeeping, remembered sets, moving things from heap to heap, just costs, because identifying the young values in this program does not help you. So if we modify this program slightly, and we discard 25% of the allocations immediately rather than pushing them through the queue, then we find, so in this version of it, 3/4 of the program, 3/4 of the allocations still traverse the queue as before, 1/4 are just dropped on the floor immediately. Now in this program, it still doesn't satisfy either version of the generational hypothesis. Most objects do not die young, most objects live for the length of the queue. And the next object to become unreachable is not the most recently allocated one, typically. 25% of the time it is, but 75% of the time the next object to become garbage is whatever's fallen off the back of the queue, which is in fact the oldest object in the system. Yet, on such a program, generational GC will tend to be effective. A young generation, even of a very, very small size, like enough to hold one object, will manage to find 25% of the garbage of this program. And if the young generation is very small, then the overhead of doing so is just one object's worth. So it's easily worth the cost. So generational GC is effective on this program, but its effectiveness is not explained by the generational hypothesis. But I made a slightly stronger claim earlier. I claimed that the generational hypothesis did not imply that generational GC was effective. So to falsify that idea, I'm going to need to find an example where the generational hypotheses are true, and yet generational GC is not effective. And so an example program along these lines was actually given by Baker back in 1993, and it's an exponentially distributed object lifetime. So in this program, we're still going to keep allocating new objects and putting them into this big queue, except instead of dequeuing them like a normal queue, we're going to select a random object to dequeue each tick, and then remove a random object from the queue and discard it. So any given object has a fixed probability of being the one chosen at each tick. And that means that the lifetime of an object, which is the number of ticks that it survives before getting deallocated, will be exponentially distributed, or theoretically, or more technically geometrically distributed, but exponential is the continuous approximation. And in this program, generational GC is not a good idea. Every object in this program is equally likely to be dequeued next, to be discarded next. So there is no benefit to identifying a particular region of the heap as the nursery, because it is producing garbage at no better a rate than any other part of the heap. However, this version of the generational hypothesis does actually distinguish the two phrasings. It's true in this program that most objects die young, but it's not true in this program that the next unreachable object is likely to be young, because most objects die young, but also each object is equally likely to be the next one to die. So we can modify this program slightly and get a version where instead of choosing uniformly at random which object to remove from the queue, we add just an arbitrarily small bias. We're very, very slightly more likely to select an object from the start of the queue, or towards the start of the queue. So this bias is so small that it has essentially no effect on the performance of the program as a whole. So generational GC remains as ineffective as it was in the previous example. And yet that tiny bias is enough to make the second version of the generational hypothesis also come out as true. The next object is slightly more likely to be young than to be old. And still, most objects die young, because in an exponential distribution, the median is less than the mean. More than half of the objects do live less than the average lifetime. So I hope these examples go some way towards explaining why I think that the generational hypothesis is, while has been shown to be generally true, it's not a great explanation of why generational GC works. So that leads to the two questions that this work raises, which is, if it's not most objects die young, what property exactly is it that makes generational GC effective? And the second question is, why does this property typically tend to hold in practice? It's been quite widely confirmed empirically that the generational hypothesis does actually hold for a lot of programs. And why is that? What is making most programs be generational? So the answers to these two questions are based around a new metric that measures generationalness of a program more directly. So this new metric G has a number of advantages over the standard generational hypothesis. First, it's a quantitative measure. It goes from 0, which is a completely non-generational program, like the single queue of the first example, up to 1, which is a program where a small proportion of the objects are very, very long-lived tenured objects, and everything else is immediately discarded. So that's a maximally generational program. And it gives every program just a number between 0 and 1 that quantifies how generational it is. It's a property of program behavior. So, of course, it may depend on the lifetime distribution of a program may, of course, depend on its input as well as its text. So it's not just a static property of program source code, but the point is that it doesn't depend on GC implementation choices. So it's not a metric like the amount of garbage collected by a semi-space collector with a 4 megabyte nursery. It's a property intrinsic to the program, unrelated to how you choose to implement the garbage collectors. And as explained in detail in the paper, it's sufficient. A high value of this metric is sufficient to show that generational GC is effective. There's a simple model of a generational collector in the paper. It has a number of caveats because it's a very simple paper model, but there's also proof showing that under this model, any program with a large enough G will have its performance improved by a generational collector. And the answer to the second question of why generational collection typically helps in practice is this result about composition. Unlike the standard generational hypothesis, this version with the metric G is compositional in that we can say something about a composed program by knowing what this metric says about its parts. And in particular, composing a program out of multiple parts tends to increase G, giving some explanation for why large programs tend to exhibit generational behavior. So what is this actual metric? Well, it's based on lifetime dispersion. So statistical dispersion measures how spread out a distribution of a variable is. The variable in question here is the lifetime of a random object. So the key idea here is that we're focusing on the distribution as a whole. It's not a property about just the young end of the distribution. It's about saying that there is a large diversity of different lifetimes in the program. Not just that lots of them are young, but that there's a wide range of them. And the exact way that this is being quantified uses some statistical tools that were developed for economics. The Lorenz curve is a completely generic piece of stats that you can use for any variable, but it was introduced for economics, and it is typically used to measure income inequality or wealth inequality. So it's this curve going from 0 to 1. It's always increasing and it's always convex. And along the x-axis, it shows the percentile rank of a variable. And along the y-axis, it shows what fraction of the total or even what fraction of the mean of that variable is achieved by that percentile. So that point that's labeled on this graph at 0.6, 0.2 is interpreted in economics as saying that this represents that the bottom 60% of households are receiving just 20% of the total income. So if there's perfect equality, then this tends to be a 45-degree line going from 0 to 1. And if there's perfect inequality, there's just complete inequality with all of the income going to a single household, then this will look like a right angle going all the way along the x-axis, then turning upwards, going all the way up the y-axis. So it turns out this tool is an excellent way of analyzing garbage collector behavior as well as economics. And that same graph, if the variable is not income but object lifetime, can be interpreted as saying the youngest 60% of allocations occupy only 20% of the memory currently in use by live objects. So that's not that interpretation is not a completely trivial step. The details are in the paper. The slightly fiddly bit is that we're taking a variable about lifetimes and we're making a statement about, so that's a time metric, and we're making a statement about space usage. And to connect those two, we use Little's law from queuing theory, which tells us that the average lifetime is going to be proportional to the average heap size, thinking of objects in memory as a form of queue. So then we can, having introduced the Lorenz curve, we can see the actual metric that I'm proposing here for generational collection, which is, again from economics, the Gini coefficient. So this is a number from 0 to 1, and it measures inequality, and it can be derived directly from the Lorenz curve. So it measures the area under the Lorenz curve, except it's scaled so that 0 is complete uniformity and 1 is complete inequality. And generational GC will become effective when G gets high enough. So if we look again at the Lorenz curve, then we measure the area under the curve, but actually G is defined as 1 minus 2 times the area under the curve. So that means when the area under the curve is large, it's a half, is the biggest it can be. That means G is 0. And when it's tiny, that means G is close to 1. So when G is close to 1, the area under the curve must be very small. And if the area under the curve is very small, then since the curve is increasing and convex, that basically means that the curve has to be tucked into the bottom right corner. And it means there will be some point along the curve close to the bottom right corner. And such a point will always represent some percentile, so that the youngest X% of allocations occupy only a small portion of the live heap. And that gives us a good generation size. If we take a generation big enough to contain only that proportion of the live heap, then despite being small, it will still be able to collect a large proportion of the total allocations. So that's a very informal argument for why a high value of the Gini coefficient will be sufficient to make generational garbage collection work. There's a much more detailed argument in the paper against a concrete model. With a number of caveats, it's a very simple model, but nonetheless a concrete model of how generational garbage collector works. So the final part of it is the explanation of why this tends to increase with composing larger programs out of smaller. So larger programs are modeled here as mixture models. So that's the distribution of lifetimes is a combination of the distribution of lifetimes of the subprograms. This works. This is a good model for parallel composition, where the objects have unrelated lifetimes, and it's a good model for sequential composition of a pipeline of stages where each stage is allocating fresh objects to pass on to the next stage. I point out it's not a good model for sequential composition where objects are being reused all the time. If each stage in the pipeline is just passing the same object along, then you'll find that then the arguments here don't apply. But at least when different subprograms are allocating different objects at different rates, then the arguments here will apply, and we'll find that the composing larger programs out of smaller tends to increase G in two different ways, both that it's bounded by the G of its parts, and also it's bounded by how different the parts are. If a composition of two non-generational parts that are sufficiently different will still be generational. So in summary, I'm arguing that a high Gini coefficient is a better version of the generational hypothesis than the standard one. It's quantitative, it's a thing we can actually measure and compare in between benchmarks. It's not dependent on a particular implementation strategy. It composes better, and it's actually sufficient to prove that generational GC works. So thank you. Think of some time for questions.
Yeah, thank you. So it's a great example of an intellectual abstract. Thank you for the presentation and work. So a question?
Yeah. Great talk. I really enjoyed that. Steve Blackburn, Google and Australian National University. Great talk, Stephen. Really enjoyed that. Just two fairly simple questions, I guess. Oh, first of all, I should say that this is, I'd really love to integrate this into our detailed analysis of the da capo benchmarks, or any other benchmarks for that matter, and just have that as public knowledge about what the G values are for the different workloads. It's be quite useful. But more specifically, you mentioned that the point about time and Little's law and so forth. Oftentimes we measure time in memory management in bytes allocated rather than on the wall clock, which perhaps would make that easier. That's one part of the question. The second part of the question was phasic behavior. That is to say, I haven't seen your paper yet, so I'll look forward to reading it. But I just wondered if you'd given any thought to, or you'd studied programs that change phases with respect to this metric, or whether this analysis allows for people to reason about how the G factor might change as a function of time.
Right, so first of all, I'd love to see measures of these in the da capo benchmark suite. So a limitation of the analysis in the paper is that I'm just assuming steady state. So I'm assuming a program with a single phase. That's partially where the Little's law thing is coming in that that's the thing that says in the steady state the average lifetime is proportional to the average heap size, and that's kind of assuming that an average heap size is a thing that exists and is constant. So I think this, it does make sense to talk about this G value changing over time, but I have to do a bit more maths to make that idea completely make sense.
Okay, hi. So it's Eres Petrang from the Technion. First question, when you say that it was not good to use generations, did you actually experiment with programs, or you just believe it will be like that? And second part of the question is there any tool that can help measuring the G value, the Gini value on a program that I have?
Okay, so first of all, it's no. This is a bunch of maths rather than empirical measurements. So for the first program, I think generational GC will definitely be ineffective in that every generational GC is ineffective when there's 100% promotion rate. You're paying all of the bookkeeping cost, but you're not getting any of the benefit. But I do want to be clear that this is the intellectual abstract property of this paper is that it is just a model. It's not been validated or anything against an empirical, against an actual implementation. So for actually measuring this precisely over programs, it's fairly so it's very easy to compute G given knowledge of the distribution of object lifetimes. That can be somewhat hard to get. It's fairly easy to get an over approximation of this by trying garbage collection at different heap sizes to see how well it collects. But there is some work on, particularly the Merlin trace tool, to give precise information about object lifetimes. And as future work, I'd really like to hook this up to Merlin or one of its descendants to actually produce precise information about the G coefficient.
Thanks very much. Yeah, thanks Jeremy Singer, Glasgow University. Thanks, Stephen. Lovely talk. I really like the idea of kind of mathematical and economic models for memory management. My question is, does your analytical model assume that all allocations are equally sized?
No, it doesn't make that assumption, but that's partially because it doesn't really come up very much. So the input to the model is a completely arbitrary distribution of the lifetime of a random byte of allocation. So if objects have different sizes, then you'll find lots of them. You will find that the distribution of a lifetime will be represented in proportion to the size of the objects allocated there, but it all just boils down to a single distribution, so the analysis doesn't really care.
Thanks.
Okay, let's thank the speaker again. Okay, so the last, yeah, please connect. The last paper for this session is Secure Mind, the framework for benchmarking large language models in memory bug detection and repair. This paper is by Huanting Wang from Wang, Jacob, David Kelly, Yehaya El Khatib, Jeremy Singer, and Zheng Wang, and they're from University of Leeds and University of Glasgow.
Hello. Okay, hello everyone. I'm Huan Ting, and I come from University of Leeds. And today I'm very happy to be here to introduce our framework Secure Mind. In this work, we design and construct a framework to help people to conduct their research on large language models for bug detection and repair tasks. And especially, we conduct a large evaluation on the memory-related bugs. We hope that our framework, our insights, can help community to design and construct a better LLMs for software engineering. Okay, first I would like to thank for all our co-authors. They are Dejis, Yehia, David, Jeremy, and John. They come from the University of Glasgow and University of Leeds. Okay, let's start from the background, the large language models for vulnerability detection. You know, when we talk about the LLM, this is a very promising and very popular technique in current world. And a lot of researchers want to use large language model in their own tasks. For example, large language model has changed the interaction method for bug detection and repair. For example, when you want to detect vulnerability, you just need to chat with a large language model. Hey, large language model, do you think there is a vulnerability in this program? And the large language model will give you the response. Oh, I think this is a vulnerability, or I think this is a benign code in the source code. So you can see it's very straightforward and very easy to use. However, there are still a lot of questions, or I would say there is a gap between the bug detection repair as well as the large language model. For example, when you want to conduct a research on large language model for bug detection and repair, you can see a lot of pipelines. You need to define the prompt, you need to extend the prompt, you need to collect enough data set to evaluate your large language model, and you need to train the hyperparameters, and you need also maybe to write the code for the management engine to assess your large language model. So it's very important to help you to save time to assess large language model for bug detection and repair. Another part is a data leakage problem. You know, for training a large language model for those big companies, there is a cutoff date. People need to, collect the data set before the cutoff date to train the model. And when you want to assess your large language model, you will also need to collect those real-world data set from just like the GitHub repositories or CVE database. And at this time, if your data set is after the cutoff date, sometimes the data leakage will increase because your data set may be trained to the large language model. So you will see a large language model will give you a misleading high precision, and which will increase inflated sense of the large language model's capabilities. So this is another problem. So what do we want to do? The first, we would like to design a framework that enables automated vulnerability evaluation of LLMs. Another part, we would like to help you to collect enough testing benchmarks which can align with real-world development, as well as which can escape the data leakage problem. And we would like to conduct a large-scale evaluation on the memory-related bugs, and we hope to share our insights to help the community to construct LLMs for vulnerability-related tasks. Okay. Now I would like to introduce our framework SecureMind. Our framework is a totally Python framework and which provides a lot of Python APIs to help you to design your own test plan to assess the large language models. You just need to define your, just like the cutoff date of your data set, and you just need to provide the LM tokens and to define which metric you want to assess to design your own test plan. By giving these parameters to our SecureMind, we will automatically help you to construct the entire workflow and execute automatically, and it will return a test report to you. You can see it's very easy to use and very straightforward, right? So let's go step into the SecureMind. First, I would like to introduce about the data side component. Here we provide 4 different programming languages, just like C, C++, Python, Java, and we also provide a compilation component which can help you to compile the C and C++ to assembly code, which will allow you to assess your large language model to those assembly code. And by defining your own cutoff date as well as the CWE types you are interested in, we will automatically collect enough testing data set from 6 different data sources, just like the GitHub repositories as well as a CVE database. And finally, we will return the vulnerability code as well as the patched code to you, which can help you to assess the large language models for your vulnerability tasks. Well, and for the prompt, we currently provide 24 different presettled prompts, and 14 for the bug detection and 10 for the bug repair. And they are some of them are very short prompts, which means we solely rely on the pre-trained large language model. And for those few short prompts, we usually provide an example which can guide the model's interface. And for those chain of thought prompt, we usually give a step-by-step instruction which can also guide the interface of your large language models. And for evaluation metrics, we provide 3 different types of metrics. The first is a deterministic score, which can measure the consistency of your large language model's response during multiple runs. And for the performance metrics, we use some very popular metrics that have been used for prior research papers, just like the precision recall, FE score, and accuracy, and which can be also extended with the help of our Python APIs. And for the reasoning metrics, which is measures the reasoning ability of the large language models. For example, one of the metrics we used is cosine similarity. We compare how different or how similar is the ground truth given by the experts, as well as the response given by your large language models. And we found how different is ground truth as well as the response given by large language models to find the reasoning ability of your large language model, whether your large language model understands the function of your programs. Okay, this is our prompt and metrics. And for using SecureMind, it's very easy to use. You just need to define your tasks in several lines of code. For example, for the parameters, you just need to provide a range of your parameters, and we will automatically to train the parameters and to construct your workflow. And for the baseline models, you just need to provide the large language model's name as well as API tokens. And for the data set, you can define your data set by giving a cutoff date as well as a specific vulnerability type. So it's very easy to use. Okay, for the evaluation setup, I mentioned that we would like to do a large-scale evaluation for those memory-related bugs. Here we provide 10 baseline large language models, include those very popular large language model, and the parameters up to 4 or 5 billion parameters, which is Llama 3. And for the data side, we provide 14,000 samples, which consists 8 different CW types, include those very popular memory-related bugs, just like the buffer overflow, use after free, double free, auto bounds read and write, and we will share our insights. We hope it can help communities. Well, first, I would like to show some insights across different props. The first, we simulate the practical situations that, when we want to detect a vulnerability for programs, we have no idea whether there is a vulnerability or which type is this vulnerability. So we just ask a large language model, hey, large language model, do you think there is a vulnerability in this program? And you can see the precision is not very high and the performance is not very well. So this is a practical problem that we don't have so many, just like the vulnerability context. And this can be solved by giving some vulnerability context, just like we adding the CW types. We ask the large language model, hey LLM, is there any double free vulnerability in this program? And you can see the precision increase 5%. So it means by adding some vulnerability context, our performance will be increased. And you can also assign a role to your large language model. For example, hey LLM, you are a security expert, and you can see the performance will increase 10%. And by giving an example to guide the large language model's interface, the precision will also be increased. And for this example, for the detection one, this is a very simple one, just like do you think there is vulnerability? And we can see the response is not very good. And for the last one, step-by-step instruction, and our large language model will follow the instructions. For example, first, is there a buffer overflow in this vulnerability? Is there use after free vulnerability in these programs? And you can see the performance will increase 10% and it will be better with the help of those chain of thought prompts. So these insights give us some ideas to improve the large language model's performance when conducting with vulnerability detection and repair problem. And across different large language models, we found that the model size, the chain of thought can help to improve the performance of those of this vulnerability detection method. And generally speaking, the model size can, a bigger model could perform better for vulnerability detection. And for different vulnerability types, we can say large language model shows different performance in each vulnerability types. The best one is a CW'25. This is double free vulnerability. And most of our testing data, the vulnerability pattern is the free function called more than once. So this vulnerability pattern is much easier to detect for our large language models. However, for the CW'119, this is buffer overflow vulnerability. And we can see the performance is not very good. That's because for the CW'119 buffer overflow, the reason for this vulnerability is complicated. For example, the improper inputs, as well as the vulnerable code could be across different functions. So these much more complicated vulnerability patterns will difficult to detect by our large language models. So a future direction for our research maybe we can help the large language model to detect those more complicated vulnerability patterns for those specific CW types. And for the low-level language, just like the assembly code, we can see that the reading score almost equal to 0, which means our large language model cannot understand the meaning of the functions, the meaning of the programs, and the performance is also not very good. So another interesting thing is we can fine-tune the large language model with the help of those assembly code to detect the vulnerability for the assembly code. And the last part for the bug repair, our repair rate across different large language models from 3% to 37%. And for those vulnerabilities that cannot be repaired by our large language models can be categorized to two standard or two tabs. The first is those vulnerability triggered via a long execution path across different functions. And another part is the vulnerabilities require patching across multiple functions. So we hold the view that the bug repair ability of large language model is limited by the long context ability interface of the large language models. Okay, you can say the large language model shows moderate success in bug detection. However, they struggle with the bug repair and just like the assembly code bug detection in bug detection. And we can say the secure mind can make it easier to help you to assess your large language model on the vulnerability related tasks. Okay, and if you want to know more about our detailed information, our data site, as well as our insights, you can scan this QR code to get more detailed information, and you can try our framework in our GitHub repositories. And I'm very happy to discuss with you about the large language models for the bug detection and repair. Thank you very much. Thank you.
Thank you. Yeah. Any questions? So, okay, yes, sure.
Martin Mas, PLDI'25. Thanks for your talk. Enjoyed it. So recently, people have started to use agents for this kind of problem. Have you thought about how your approach could be extended if you give an LLM the ability to, say, call tools and repeatedly iterate?
Oh, yeah. Currently, our framework is intended to help our researchers save their time to construct the entire bug detection or bug repair workflow. And next step, we would like to, to construct a meta framework that can help you to tune the parameters as well as to help you select the probes, which can also, save more time for our researchers and programmers. So it's very important to, construct a good framework for our users. Yeah, it's very important. But currently, we just, conduct research on the bug-related works. Yeah.
You have time for one more quick question. Maybe so do you think adding some information from a control flow graph or some static analysis could help, this process could help the LLM do anything?
Yeah, this is a very good question. I do think the control flow or those graph relationship information can help to improve the performance of those large language models. However, currently we just use those, we just constructed the workflow for the large language models, and we didn't conduct research on the just like the fine tuning or pre-training the model. So, but for the program representation, we have conducted some evaluation that more information, of course, it can improve the performance. However, currently we just focus on the, the help user to construct their workflow. But we didn't support some just like the fine tuning problem. But we will do that in the future. Yeah.
Okay, so thank you very much.
Thank you.
And, this concludes the session, and we're going to lunch.
Yeah, so lunch is together with the rest of PLDI. We'll reconvene here at 2 p.m., I believe.
Thank you for the introduction. So yeah, I thought I'd talk a little bit about some insight from industry working on the industrial side of things. Before we get too much into that, I have to show this safe harbor statement that essentially says that I am not going to commit to anything for our products relating to this presentation or something like that. Okay, so first thing I'd like to talk about is evolution. GC has evolved a lot over the years in OpenJDK as well. We have the serial collector, and it's old now, but it's still pretty good for constrained environments where you don't have many hardware resources. And then we have the parallel GC, which is still pretty good when it comes to maxing out throughput, but comes with latency concerns. We had CMS, concurrent mark and sweep, but retired it in favor of G1, which is more of a balanced collector that tries to find a sweet spot between throughput, latency, and memory. And that makes it a pretty good default collector. It's not the best at anything, but it also pretty good at everything. And the latest incarnations are concurrent collectors. We have Shenandoah and ZGC. And here the aim has been primarily reducing latency and improving scalability. So yeah, it's been great to see all this innovation, and I'm also thankful to the research community for playing a big part in developing new GC algorithms. And since the behavior of the GC has a pretty big impact on the behavior of Java application, it is pretty important with all of this innovation. Evolving GC, I think, requires planning. It turns out that building a production garbage collector and taking it all the way into production and sorting out all the performance issues and stuff takes about 10 years. And during this time, the market has time to change, and there's a new situation, and suddenly you find that, oh, well, now we need another garbage collector, and so on and so forth. Happens again and again. And it turns out that there isn't really one GC to rule them all, so it's pretty important to consider the different trade-offs, and it takes time to get it right. And because of this, one of the key aspects to succeeding in the long term is planning for the expected, unexpected garbage collector that you will find down the road. And it might have entirely different constraints. So one of the things that you really want to avoid in order to get that is exposing GC implementation details. And for example, the address of an object, don't expose it. The field addresses, even the offsets of fields or the size of objects, the format of pointers, all of these things, by exposing them, you're locking in the GC in some kind of GC jail where it cannot evolve. And it might make some native call 10 nanoseconds faster, which seems really great in some micro benchmark, but the reality is that you've locked up the GC here, which might be a much larger problem. And I think that one of the successes of garbage collection in Java really is because we've done a pretty good job from the start of encapsulating the GC implementation details. With the Java native interface, there's a level of abstraction. You calling functions to mutate and the state of objects and things like that. And Project Panama has adhered to similar constraints. We're not exposing things, and this allows a GC to evolve. And also inside of the JVM itself, being part of building something that I call the Access API inside of hotspots. It's an API for performing memory accesses with declarative semantics. So rather than saying do pre-barrier or post-barrier, whatever you think that a GC needs, instead it's more high level. It's a load, it's a store. What's the memory model? Is it sequential consistency, or what kind of memory ordering constraints do you have? As well as if you have a reference, is it a strong reference? Is it a weak reference? This sort of thing. So it's an API for communicating semantics from a front end, what is my expectation here, to a back end. And this allows building new garbage collectors. And yeah, I'd like to just do a little shout out. I appreciate the efforts from the C, Ruby, and Julia papers that we saw this year trying to break out of this GC jail. It's been fascinating to see. Yeah. So I mentioned that it takes 10 years to get a GC all the way into production and make it good. So then you might wonder, why is it that it takes so long? You think, yeah, I have this simple algorithm and just gonna mark some objects and throw away some garbage. How hard could it be? And it turns out that the GC interacts with a lot of systems within the JVM. You have JVM TI, debuggers, you have monitoring serviceability, and there's 3 different just-in-time compilers and 2 interpreters, the runtime, and the JITted interpreter we have is JITted for multiple different processor architectures, and then you have to implement stuff for all the different processor architectures. And that goes for some of the JITted code as well. And then you have things like class loading and unloading that interacts with the GC, and reference processing. That really complicates things, especially when it comes to concurrent reference processing. Once you've gone through all of that, then now we start having startup and warm-up mechanisms to start a VM faster, and once again there's a whole bunch of GC interactions. Even virtual threads has a lot of GC interaction. It was actually most of the work was just dealing with all the GC interactions. And then of course, other than dealing with all these issues, you still have a lot of corner cases to think about in terms of out-of-memory handling, and why is this performing 1.3% slower in Windows since some random build, and these sort of kind of boring issues, but things that need to be sorted nevertheless for a production garbage collector. So because it takes such a long time to build a production garbage collector, it's increasingly important to think about the problem domain and make sure that if we're gonna spend 10 years building something, it better solve a problem. So while it's still good to make a brilliant solution for a small problem, it's more important to even have a primitive solution to a big problem. So ideally you want the sort of solution domains and the problem domains to intersect so that the thing you're solving is a genuine problem. And on that note, I think it's worth thinking about the environment, because in reality people are running in some specific environment, and since each garbage collector has a trade-off, you have to consider what kind of deployment would I like to optimize for here? What problem am I solving? And well, then it comes to memory scaling. And let's talk about that a little bit. A lot of the JVMs run on machines with DRAM. You have some kind of computer, has some DRAM. And the main thing to consider about DRAM is that it isn't SRAM, it's really cheap. And I think the price here of DRAM really matters for the problem domain. So I've incorporated here a little chart showing the DRAM price per gigabyte since 20 years back. And as you can see, it's sort of converging on the very low end there. So let's look at some environments. If you have a laptop at home, maybe you have a MacBook or something, you might get between 16 and 24 gigabytes of DRAM. And this, if you scale it to the number of cores, is 1.6 to 2.4 gigabytes per core. And even an iPhone has 1 gigabyte per core. And with a Samsung Galaxy nowadays, you get 1.5 to 2 gigabytes per core. Of course, there's some more smaller devices. For example, the smallest scaling you can get for a Raspberry Pi 5 is half a gigabyte per core, but it scales up to 4 gigabytes per core. Apple Watch, half a gigabyte per core. Usually these small devices isn't really where we make Java deployments, but they're there. but the most common deployment type is to some form of computer. And nowadays, people really like using someone else's computer in the cloud, and we have various cloud vendors, and I got, in this example here, I have listed Oracle, Amazon, and Google Cloud, and they all have AMD, Intel, and some kind of ARM instance that you can buy. And what they have in common here, as you can see, is that you sort of get 1 gigabyte per core at minimum. It's not possible to buy less than that. For some instances, for example, here we have the Amazon Cloud, Intel instances, it's at least 2 gigabytes per core. And Google Cloud Intel instances looks like it's also 2 gigabytes per core. And there are even some names for this that, if you're talking about compute intense instances, they're the minimally scaled instances that have 1 gigabyte per core. General purpose instances have at least 2 gigabytes per core, and memory intense instances have at least 4 gigabytes per core. And now, of course, you have containers. People run things in Kubernetes and things like that. We have smaller amounts of memory, but then you also have smaller amounts of cores. The scaling is still based on these machines because you're running Kubernetes clusters on these cloud machines. And in the Oracle Kubernetes engine, seems like the smallest container you can buy is half a gigabyte of DRAM, and that's using only 12.5% of a core. And it's the same number for Amazon's Fargate, which is a similar Kubernetes engine there. And so you might be wondering, why is it that we get at least 1 gigabyte per core? Well, if we look at the different shapes we can get in the Oracle Cloud here, this is the cost distribution if you're buying 1 core with 1 gigabyte of memory. That it's, as you can tell, it's predominantly CPU, the blue stuff, that costs, and the green is memory. So at this scaling point, even if you go less, the overall cost saving is pretty small. So that's why smaller memory scaling than that isn't really available. So my main takeaway here is that if you're deploying a Java application to some kind of computer, then you can expect a reasonable minimum heap sizing or memory availability of 1 gigabyte per core, right? So let's talk about moving tracing GC. In OpenJDK, all of our collectors right now are moving tracing garbage collectors. So there's serial, parallel, G1, ZGC, and Shenandoah. And the thing about moving tracing collectors is that since you're only paying for the live stuff and not for the garbage, that means that you have a trade-off between memory and CPU. So you can choose which one you pay for. And remember then that memory is pretty cheap. So I sometimes joke about how DIMMs are the best hardware accelerators for GC. You just take a DIMM and plug it into the heap, and suddenly all of your GC worries just go away. And with the 1 gigabyte per core scaling that you get at least, it turns out that's quite a lot for a lot of workloads. So something that I sometimes see maybe a little too often, a story being told, is you have an evaluation, you have a 16-core machine with 64 gigabytes of memory, and then you're trying to run with number of benchmark threads equals to the number of cores, so you're utilizing all the CPU. But the minimum size you could run this thing on was 149 megabytes. And the way that we're exploring the CPU versus memory trade-off is by multiplying this size by 6. Then we stop there because 6 sounds like a lot. But, and with that rationale, you'll often find that concurrent GC seemed like a bad idea, and the rest of the OpenJDK collectors also perform quite poorly. And then there's a proposed solution that improves on this GC overhead, and it looks great. And you can sort of visualize the reasoning here. It looks compelling that on the left-hand side there you see the minimum heap size of 149 megabytes. And when you add on 6 times more memory, you see all the wasted memory there in orange. Sort of looks like a lot. But unfortunately, I think what happens in reality is that we've tried using between 0.23% of the available memory to 1.36% of the available memory. And at the same time, we've been using 100% of the CPU resources. And this gives us a pretty significant blind spot for what happens if we scale further. And spoiler alert, it does change quite significantly if you use only a handful or maybe 10% more of the available memory on the machine. So yeah, I think this is a bit problematic and a bit of an error mode to run in this way. And we can optimize further for this mode, but I'm not entirely sure why. So from my perspective, looking at this, what I see is, visually speaking, more like this, that we have, this up to 6 times the minimum heap size. But for me, with the sort of deployment kind of perspective, the wasted memory isn't the garbage inside of the heap, it's rather the unutilized memory on the machine that isn't being used. So the thing about having a two-way trade-off between CPU and memory is that you're always wasting something, right? Because if you're wasting less memory, then you're typically using more CPU instead. And since memory is cheap, it's pretty useful to be able to go in the opposite way and wasting more memory to save CPU. So in a way, wasting memory and utilizing memory is sort of the same thing looked at from different perspectives. So an alternative way of looking at whether you can save memory in your system in terms of actual cost is to check what happens if I run with 1 gigabyte per core, 2 gigabytes per core, or 4 gigabytes per core. Because if you can take your deployment off a 2 gigabyte per core machine and go to 1 gigabyte core machine, you might be able to save 5% cost, which is a real win. So my point here is not just that the levels are discrete, but that the lowest level is still pretty big. So we take the same experiment and use the 1 gigabyte per core scaling. It sort of looks like this still, that we end up not using more than 5% of the machine capacity. So some main takeaways about this is that when you have a moving tracing collector, garbage is something that makes it CPU efficient. And this is great when you have memory availability. And typically you have at least 1 gigabyte per core if you deploy into some kind of computer. And I think this is one of the successes of moving tracing collectors and why all of our collectors are moving tracing collectors in OpenJDK. And when it comes to this minimum heap sizing, to be a bit wary of relative differences. For example, 5 megabytes compared to 50 megabytes is a 10x difference, but 50 megabytes is overall a small amount of memory, and that utilization isn't necessarily waste. Let's talk about CPU scaling a bit. So when you add on more cores to a system, what happens when you have a garbage collector is that you induce more allocation rate. So if you have 1 core, might be allocating 100 megabytes per second. With 10 cores, we're talking about 1 gigabyte per second. So it really adds on allocation rate. And the allocation rate scales the frequency of GC as well. So if you have 10 times more allocation rate, unless you do something about the heap, you're going to have 10 times more frequent GC. And that's in turn affects the amount of work that we have to perform in per unit time. So 10 times more GC, well, that means 10 times more GC work as well. So just playing around with some mathematical modeling here, if we have a 298 megabyte heap and half of it is live, and we have 256 megabytes per core allocation rate, then you can see here that at one core we have, well, less than 1 GC per second, and as we scale this up to 64 cores, we start getting to over 50 GCs per second. So that means you have to GC like every 20 milliseconds or something to keep up, which is starting to become problematic. And since this is just a bunch of math now, there's nothing stopping me from scaling it further because there's no cost attached here. So if you have over 30,000 cores in the system, you might have to perform nearly 30,000 GCs per second, and that's like every 30 microseconds or something, which is clearly gonna be problematic. So if you're scaling the live size with some constant that doesn't depend on the number of cores, you can end up with a lot of trouble. And this is what I would think about as an error mode as well. And it's more useful, I think, to think about how much memory do I need per core in order for efficiency to look good. And for example, consider that you're using 100 megabytes per core, which is typically less than 10% of the memory availability, and add that onto the heap as you scale up. It might look something like this, that you start off with a significant part of the heap being bloated, and then as you add on a core, you're adding more bloat, but it's a relatively smaller part of the machine because we double the machine capacity. And then when we double again, we get yet more bloat, but yet lower fraction of the amount of memory being used. If we plug that into my mathematical modeling here, we find that we sort of converge to about 2.5 GCs per second instead of, I can't remember, was it 30,000 or something? So it really helps to add some amount of memory per core when you have a moving tracing collector. And another thing worth talking about is generational GC. We talked about this generational hypothesis. Most objects die young, and things that survive tend to live longer. And this is particularly useful for the moving tracing collector. Imagine that you have an application where the residency grows with the machine. It might be that you have some kind of caches, an in-memory database, or some kind of large data structure that scales with the machine. Then this can really help because most of the residency is old objects as opposed to young. And the thing about memory bloating is the amount of bloating you need to stay competitive is proportional to the liveness times the allocation rate. And that means, because it's a multiplication, that if either side here is any of the factors are small, we get a result that's small. And it turns out with generational collection, you typically get one of them being small. Let's look at an example here. So if you have a young generation, the dark purple here shows what's live, and the light purple shows the garbage. As you can see, it's a large ratio of bloat that we're adding on to stay competitive. But since the live data was kind of small, that means that the overall memory on the machine is kind of small. Whereas when the residency grows here, and is primarily old objects, then even though there's a lot more live data, the allocation rate in the old generation is much, much lower, and therefore we can get away with bloating a lot less. So in a way, generational collection really helps with the scaling here. Although there's still room for improvement here, that there is quite a bit of bloat here when you scale up the residency. But it's staying reasonably compatible, competitive, I think. Now, consider that you have an application that doesn't have some kind of cache or in-memory database or large data structure that grows and becomes gigabytes large. Then what we typically see is that the level of problem we have to solve is also quite a lot smaller. So visually it might look something like this, that we have a pretty good GC efficiency at this level, and the rest of the machine is just unused because we don't need more memory. But then if we have a deployment, we're probably gonna use it anyway, because why not? And when you do, the GC efficiency goes really low. So main takeaway here is that generational GC scales pretty well, and in particular it scales well when the problem is the biggest. So when you have a lot of residency, then it scales very well. If you don't have a lot of residency, well, it's less of a problem. So it allows residency to stay pretty competitive, even when we have a lot of objects. And because of this, all the collectors in OpenJDK are generational. Serial GC is generational, parallel GC is generational, G1 is generational, and ZGC has become generational since JDK'21 with JEP 439 that introduced a generational mode. And now very recently, Shenandoah also integrated their generational mode with JEP 404, which I nearly didn't see for some reason, but yeah, they shipped it for JDK'25, and yeah, this allows us to enjoy the benefits of moving tracing GC while solving some of the allocation rate and residency problems you get when you scale up. Let's talk a little bit about latency as well. So latency really matters when you have an interactive application. And as it turns out, interactive applications are quite common in Java. You might have a web service, or you might have some microservice. Who knows, maybe there are games as well, or less so maybe. But basically any system that interacts with a human. There's a human somewhere that presses buttons and expects a rapid reply after that. Now these response times you get in a system like this have a sort of a distribution that can be modeled and understood with percentiles. So if you have for anyone that hasn't seen this before, P50 means essentially that if you have a P50 that is 10 milliseconds, it means that half of the requests perform at least as fast as 10 milliseconds. And P90 means that if you have 20 milliseconds, P90 means that, well, 90% of the requests respond at least as fast as 20 milliseconds, and so on. And the higher percentiles we call tail latency. Something that I think has made latency increasingly important is a trend in the industry to move over to microservices. And with microservices, you run into a situation that I call latency propagation, where for each external request that comes into the system, it calls out to like 20 different microservices. And each node along the way, if either one of them has a latency issue, it propagates across the entire system back to the external request. So if you had some kind of GC problem that caused P99 noise across these microservices, then the external request is going to observe that as a P82 problem. And if you have a P90 problem, well, then you have a P12 problem externally. So you can expect that anything that's a P90 problem is going to be a massive problem for external requests. Visually, you can look at it sort of like this. Here we have a request coming in from the left, and it calls out to a whole bunch of microservices, and all the way to the right, where you see the red arrow, there's one microservice that isn't responding rapidly, and because of that, we get problems all the way back to the external request. So what can we do about it? Well, we can either accept that the latency is bad, or we can start canceling requests based on some timeout factor that if this takes too long, we're going to have to stop it and redo the work. And redoing the work wastes CPU because suddenly you have to do a bunch of redundant work. And the other approach would be to try and improve the tail latency instead. And here's an example of what it looked like for Netflix. This was when they changed to use generational ZGC in one of their services at JDK'21. The white lines there show the error rate of their requests from the day before, and the purple stuff shows from the current day that they're measuring. And as you can see, at about 4 p.m., something like that, that's when they started using generational ZGC instead, and the cancellation rate there dropped quite significantly. And it turns out that they had a bunch of latency problems in the actual application as well that they weren't even aware of because the GC was so noisy that everything else was just not visible. Okay, so if we want to solve latency, what should we be looking for? What causes latency? And we have some usual suspects: stop the world, garbage collection, we've got oversaturated CPUs, but also startup and warm-up. And we try to solve these things as much as we can. So first of all, let's talk about stop the world garbage collection. Obviously, if you stop all the application threads, those users that I was talking about that click buttons, they don't stop clicking buttons. They continue clicking buttons while the world is stopped and requests pile up. So while the world is stopped, requests pile up, and when you start running again, you have to work through all these requests that you haven't been handling, which can be problematic and cause latency spikes. And what you can do about it in a stop the world setting is try and use parallelism, throw as many threads at the problem as possible, and hope the parallelism scales. But it might be that the object topology doesn't allow for scaling. For example, if you have a huge linked list, that's not going to scale. You might also have problems if you have neighbor processes that you care about. Typically you don't, but in some scenarios you do. Then the noise caused by stop the world GC on the rest of the processes might be significant. Okay, let's talk about CPU utilization. That's another big factor in latency. Why does high CPU utilization cause latency issues? Well, I think it can maybe best be understood by thinking about if you go into a shop where there are 2 cashiers and there's an average utilization of 50% of the tills people go in there, but you'll find that some of the time there's no interesting activity going on, and sometimes there's a bunch of people coming in, and then suddenly there's a queue build up. And this randomness is really what's causing the issue that latency builds up. So if you had a mental model of 50% CPU utilization looking something like this, that half of the cores are working all the time, half the cores are just idle, that is the case when you have a parallel workload. But with an interactive system, it looks a bit more like this, that some of the time all the idles are, or all the cores are idle, some of the time they're all working and their tasks queued up, and sometimes there's something in between. Overall, you get 50% utilization, but there is also a bunch of waiting involved. And there's people in queuing theory that thought a lot about this over the years, and can do some mathematical modeling of the probabilities of how long the expected waiting times are, so on and so forth. Have this simple model called MMC model, where you can model if you have C different servers, what will be the expected waiting times given different utilization rates, and tried plotting this here. And if you look at the orange line there with one core, you find that the expected time to process grows quite a lot faster than all the other ones. And for every core that you add on, you get lower waiting times for the same CPU utilization. So the trend here is that the higher number of cores you have in the system, the lower the impact of the expected waiting time with a high CPU utilization. And this isn't just some theoretical mumbo jumbo, but something that we also see in practice. So here's an example of what it looks like in Spec JBB 2015. As you increase the injection rate and the more requests being served, we can see that latency gets worse. In this case, the blue there at the bottom shows the P50, which is sort of the median, and you can see it grows with the CPU utilization. Then the green is the P90, yellow is P95, and the pink is P99. And they all sort of get progressively worse as you reach the highest level of CPU utilization. At the end, you could sort of fall off a cliff. So some takeaway there is that if you have an interactive system, you probably don't want to run it on 100% CPU utilization, because it will be kind of disastrous for the latency. And this is not a way that you would run things in a deployment. You would have a load balancer that scales out and keeps the overall CPU utilization much lower. Now, exactly what level you'd end up at, kind of, as I discussed, depends on, for example, how many cores and the application itself and things like that. But something much less than 100% anyway. So again, we can optimize for this, but sometimes it might be that optimizing for some kind of error mode ends up performing worse in a situation that's more realistic. So yeah, your 75% CPU utilization might look problematic on a small machine, but might look totally fine on a large machine. Yeah, and it helps to be able to scale to larger machines if you want to keep the latency low because of CPU utilization. And even on the small machines where you have to have lower CPU utilization, it might be that you get more memory per core instead because you're utilizing less of the CPU. Okay, so since the CPU utilization is something that impacts latency, that's something that's been on our mind quite a lot, building a low latency GC, that we have concurrent threads, and if you put too many concurrent threads in there, start running concurrently, then you're increasing the CPU utilization of the machine, and the end result of that might be that you get a latency problem. So you have to really consider how many GC threads you should be using. And it turns out that if you want the maximum amount of GC throughput, meaning that you want to free up as much garbage as possible every GC cycle, then what you want to do is to wait until very late to start running the GC, because the later you wait, the more garbage is built up. But then when you start the GC late, that means you have to throw in a lot of threads into the system to manage concurrently collecting before you run out of memory. And the impact of that is you get this spike in CPU utilization, which causes tail latencies. But it's great for GC throughput. So if you want better latency instead, what you do is sort of the opposite, where you try to start a GC much earlier instead. And by starting it earlier, there's more time to perform GC, and you can run with a single thread instead, which is causing a lot less noise in the machine, and it tends to go under the radar in terms of your percentiles. But it does mean that you have to spend more GC CPU cycles to get the same garbage collected. But since we have a low latency collector in ZGC, this is the approach that we've chosen. We try to use as few threads as possible and start earlier rather than later. Avoid all the CPU bursts and yeah, make sure that latency problem is solved. Okay, so some summary here, some of the main takeaways. Maybe the most important one being that if you want impact, then try to solve things that are problems. And in order to do that, it's quite useful to think about the problems and think about the kind of deployments that people have, and whether, you know, just think about some examples at who's going to be using this feature. Is it someone deploying in a Kubernetes pod or cloud, or what kind of environment do we have? And then think about whether this solution matches that. Yeah, and try to also be wary of error modes and optimizing for that, because it might be that people don't really do that. And the thing that people do might end up getting worse. So DRAM scaling, DRAM is quite cheap, and computers get at least 1 gigabyte per core nowadays, and adding a couple more gigabytes per core is still pretty cheap. And when it comes to CPU scaling, in a similar way to how you would scale the number of threads from 1 to the maximum number of hardware threads, similarly with memory, it can be quite useful to consider what happens when you use all the memory on the machine, and also consider different levels of memory scaling there with 1, 2, or 4 gigabytes per core, because that's when you can really save money. And latency, well, latency is important, and something that is the driver for load balancers. And unfortunately, it's quite hard to find benchmarks where we don't try and use 100% of the machine, which makes a lot of sense for batch jobs and that kind of workloads. But for interactive systems, that really isn't what we want to be doing. So something to keep in mind. Try to use lower CPU utilization and see how does the system perform under a reasonable level of load. Yeah. And finally, the most important thing is, if we're wondering which is the best garbage collector, is of course ZGC. But apart from that, it might depend with it, the trade-offs and what you're actually doing. But in general, ZGC is the best. Okay, thank you very much.
Thanks for a really interesting talk.
Thank you.
Have any questions?
So, thank you, Benjamin from ANU. So you've been talking about giving some memory per core, but I know some of the jobs that some programs do are not CPU bound. So, but in recent years, if I remember correctly, OpenJDK gained the feature of virtual thread that can run, that can do better job at multiplexing multiple jobs into one single core. And what do you think is the impact of this recommendation if the one core can do multiple jobs at the same time more efficiently?
So my main recommendation is to look at the problems and then find a solution based on that. And if your workload has that kind of nature that it's not CPU bound, but you're rather thinking about how many VMs can I stuff into the same machine that are mostly idle or something like that, then absolutely that's worth looking into what kind of solution would match that problem.
Eros Petrang from the Technion. So you're saying it takes 10 years to build a GC and then you discover you want something else.
Yes.
Maybe it makes sense to have different kinds of GCs, and then after 10 years you discover you want something else, you have it. You just need
Oh yeah, that's exactly what's happening right now, actually. Because now when people are running very small workloads inside of small containers, they're asking for something that works well on the small scale. That's sort of what we started out with, and it turns out serial GC is not too bad in those situations. And I ask people who run this kind of stuff if they have any GC problems, and turns out the main problem is figuring out what heap size to use, but otherwise they don't really have that many problems.
And what about having reference counting as another option in your, you know?
I think reference counting is very interesting, but I think that the place for it might be not among newly allocated objects, but among older objects. But it's something that is being considered for sure, yeah.
Okay, thanks.
Hello, Jeremy Singh at Glasgow University. Thanks for a really nice talk. I think automatic memory management is becoming increasingly deployed on microcontroller devices with very constrained memory and much slower CPUs. Do you think, I mean, the numbers are different, but do you think your recommendations would be different in that domain?
Yeah, absolutely. So as I said, it all depends on your deployment situation. Yeah. And I've been mainly talking about deploying to some kind of computer. Whereas if you're deploying to some very small, like embedded device or something like that, then yeah, it very well might be that you want an entirely different solution. So you used to have a Java embedded, I suppose, and still some similar stuff going on. So yeah, definitely, if you have a deployment environment where you want very small things, then that is definitely something to consider. But you probably won't have like 32 cores running around in those controllers. So that's why it's sort of important to think not just about whether it makes sense to save memory, but about the actual scaling of CPU versus memory. And I think that still holds.
Martin Maas, Google DeepMind, really fantastic talk. I really enjoyed this. You had this great observation about that it's not just about the absolute amount of resources that are being used, but also about the amount that's left and unused. I'm curious how you think about feedback loops. So for example, you're trying to use all the memory that's available, and then a hardware vendor might look at this and say, okay, this workload takes 1 gigabyte, let's just to be sure give 2 gigabytes. The next iteration of the workload takes 2 gigabytes. How to avoid that feedback loop?
So I don't know if it's a feedback loop or if it's just economics, that if you looked at, you know, the cost of memory versus CPU, that when you get to like 5% of the cost is memory, then even though it turns out very few people are using that extra memory, then the actual savings of not having it there isn't really that big anyway. So I think it really comes down to the economics, that if the memory starts costing a significant enough portion, it makes sense to use less, but otherwise it might not, even though it's wasted.
Makes a lot of sense. Thanks.
Thanks.
Thanks. If I could, kind of following on from Martin's question, something I was reminded of. There's a very nice paper by Gernot Heiser on benchmarking crimes, and he identifies some common things that people do in systems papers in the evaluation that are like really bad. And it sounds like you've got some ideas about garbage collection benchmarking crimes, like looking at heap sizes that are not representative and looking at particular workload mixes. I was wondering if you had any specific ideas there on what we as a community should be striving to avoid doing ourselves and discourage people we see.
Yeah, certainly there's a bunch of stuff there, and I think though thinking about the memory versus CPU scaling and whether it makes sense for the kind of machine that you're running on. Like if you're running on a large machine, then it probably makes sense to use it, and if your target is something small, then you should probably be running on something small to see how it actually behaves there, instead of interpolating that it will probably be the same. and that kind of thing. But also, when it comes to the latency, to look rather at what kind of latency distribution you have at different levels of load, instead of picking one where the one you pick is the worst looking one, where the CPU is oversaturated, which you wouldn't really do. Yeah, I think those might be some of the main things to consider. I know there's difficulty also in it's not easy to write this kind of benchmarking tools and stuff, and there's always some factor of being more exact versus convenience, that you can have the most perfect system where now you're measuring every single digit perfectly, but it takes 10 weeks to run it, and it might be a problem as well. So I think I mostly have thoughts about the problem space, and when it comes to the solution space, it is definitely a bit of a trade-off there between doing it right and doing it in a timely fashion and being pragmatic.
Start at the back and go forward.
So I found your discussion of the common kind of error in research of interesting, where people kind of stop after 6 times the minimum heap size. So I'm a little bit of an outsider, but I don't think that comes from nowhere. I mean, I think there was a prominent paper from a while back that said that where the take-home was, kind of 6 times is enough, right? You don't get a lot more performance, CPU performance from adding more memory after that. Is that, I realize these things are often dated. Is that one out of date?
So, I think, Steve, I think you were on that paper. I don't recall if the paper's main takeaway was that you should have 6 times the min heap. I think it was that you should be looking around for what the memory versus CPU trade-off is and try different heap sizes. And I think there was more of an example in that paper that it used 6 times the heap size. But I think maybe some people read that and thought, oh, so what you're saying really is that it should use 6 times the heap size, and then that's become a trend, and that's what we're seeing now. But I think that the main takeaway of, make sure that you're looking around at different heap sizes is definitely still a good recommendation. Yeah.
Thanks. And I think implicitly you're saying sometimes I do need more than 6 times to get good performance.
Yeah, absolutely, you do, especially on the small scale. And on the larger scale, maybe less so because of generational collection, but on the small scale, when you have very small residency, it might definitely be that you need more, because you have to account for the allocation rate of all the cores. That might be a very large proportion to the heap size at that rate. Yeah.
Steve Blackman, Google DeepMind. Thanks, great talk. Very interesting and thought-provoking. But I particularly enjoyed the commentary you gave about the context and how important that is. Just a very quick response if I made it to Jonathan's thing. I think partly what that was with certain algorithms, you get an asymptotic return on it for a given, and that for many algorithms would bottom out at 6x in that paper that you were referring to. But in a different context with a different algorithm, that may not be so. So I think you'd need to reevaluate it in the appropriate context.
Yeah. Yeah, I think that makes a lot of sense. And something that sometimes I think hard to talk about in an academic context is dollars, because it might be when you get some kind of asymptotic diminishing returns, that even though you have a very small amount left that you can reduce by like doubling the memory, it's without thinking about the scaling to that memory and CPU has to money, might look like seems entirely unreasonable to double the amount of memory just to use 10% less CPU. But in terms of cost, it might very well be worth it. But yeah, I don't know. It's also science, so we have to think about the resources, how they relate to each other, not just dollars. That's where I come from in industry. Think about dollars, but there's more to it.
The actual question I was going to ask, and this is very open-ended, so I don't know how you want to respond to this. In my experience, both in the academic world and in industry, I often find myself talking to people who don't want to hear about GC, who are not, they're not believers in GC, and then they will often frame their critique in terms of how a C++ program that did this similar thing would behave. Right? And then they would measure the failure of GC with respect to CPU and memory, and particularly memory, and say, oh, well, you know, our C++ runs in much tighter heap, blah, 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 blah. So at one point in your talk, I was just beginning to think, well, what would those people say to this position? And I guess that's kind of my question. Do you have any thoughts on that?
Oh, I do have thoughts. I have thoughts about a lot of things. So a different way of thinking about it, if you have a C++ program where you're able to run with only 50 megabytes, but you're still running on a machine with 32 cores, and you have 32 gigabytes of memory, then, you know, while you're using a lot less memory here, because there's no garbage, you're also inducing CPU waste every time you free memory, because when you have explicit memory management, you're paying for all the stuff you're freeing. So in a way, it's kind of a lost ability then, that you can't use the remaining machine memory that's there anyway. So you paid for the memory, it's there, and if you're not using it, it just means you're wasting CPU and freeing stuff, whereas the GC will just say, oh, whatever, let's just bloat the whole thing and just remove all the CPU overhead, and the GC is going to cost pretty much nothing, and then call it a day. So I think that there's a difference in how you look at it, that whether the important thing is bloating memory or bloating CPU. And since CPU is the more expensive resource, I tend to think that reducing the CPU is worth quite a lot more.
Yeah, totally. I totally get that. But just to refine my question, I think a lot of those folks would frame it in terms of the CPU and say, oh, the GC is really expensive with respect to CPU compared to my C++ program.
Right. And yeah, I don't know how much I can talk about this, but let's say that I've seen systems where using something like Rust or something like that, and yeah, sure, it might be that you can get about twice the amount of density in a cache, for example. And I think that is definitely an area where we can improve, is to beat native manual memory management in terms of density as you're building data structures that actually scale up to a large portion of the machine. And these kind of systems also tend to be quite costly. So even though not everything is a cache, it turns out that things that are a cache cost a lot of money when you have, like, we're talking petabytes kind of deployments. It's very expensive, and improving the density of data in those kind of deployments, I think there's a real win there if you could get that down compared to Rust and C++ and stuff like that.
Right. Well, let's thank Eric again for a really interesting keynote talk.
Thank you.
Okay, and the second presentation in this session this afternoon is going to be our Best Paper Award recipient. So very pleased to confirm that this year's best paper is going to arborescent garbage collection, and presenting it today will be Leonard West O'Leary. Apologies if I've not got my pronunciation as good as I could, but thank you again for choosing to submit to ISMM, and we look forward to hearing about the work.
Thanks a lot for choosing us as the best paper. So hi everyone. A little bit of pressure because so today I'm going to present the arborescent garbage collection, a dynamic graph approach to immediate cycle collection. So this is joint work with Frédéric Lahaye-Bertrand, Olivier Melançon, Marc Filet, and Stéphane Monnier, It was really a pleasure to work with them on this new garbage collection algorithm. So our problem for today is collecting cycles immediately. So what do we mean by immediately? We mean that the garbage is collected as soon, actually before any other operation by the mutator. So in other words, it's done before we go back to language space. And if we look at commonly existing techniques, there is tracing, which can collect cycles but do it in a deferred way. And there is reference counting that can collect garbage immediately in our sense, but doesn't collect cyclic structures. So why do we want to collect cycles immediately? There's a couple applications that are interesting, but most of them revolve around finalizers. So doing something when a certain part of memory is removed. And for example, if we had the ability to collect all garbage immediately, we could interpolate with a garbage collector with, for example, C++ or Rust destructors. So our approach here consists of first of all modeling the heap as a reference graph. So here, the graph that we see, each node represents an object in the heap, and links between them mean that they have a pointer pointing to it. And what we will do is we will embed a spanning forest within this this reference graph. So, and if we think about it, the problem of garbage collection can be seen as finding a spanning forest starting from the roots, and all nodes that are part of this spanning forest are actually reachable, and we can collect all of the other nodes. So here in the graphs that I show, each edges in black here will be part of a spanning forest, and the one in gray will be part of the reference graph. And our approach will be to maintain the spanning forest during the execution of the program. So while the program executes, we will remove and add references. This will correspond to changing the graph. And our goal would be to rebuild this spanning forest while we are executing. So now let's go over some definitions. So here we will model the roots or the uncollectible nodes as yellow in the graph here. If we have a black edge, we will call nodes between them as having a parent and child relationship. So for example, D here would be the parent of G, and G would be the child of D. And we will add another relationship, which we will call the co-parent and co-child relationship, which is relationships between edges that are not part of the spanning forest. So for example, here B would be the co-parent of G, and G would be the co-child of B. So our work is inspired from ES trees. So I won't pronounce the word here because I'm not exactly sure how to pronounce it. So I'll say ES trees for the rest of the presentation. But ES trees are a data structure that are that is used to maintain a minimal spanning forest. And it has been developed in the field of dynamic graph theory. And it uses a notion of rank to keep this distance. So at each moment in time, it keeps a rank for each node, and it changes it and recomputes the rank as the graph changes. And we will see how we will use this notion of rank to create our algorithm. And also, in the case of ES trees, ranks are strictly monotone, so always increasing in increments of 1. However, in the case of garbage collection, we don't need a minimal spanning forest. We just need a spanning forest. And as long as we have one, we know that all nodes within the spanning forest are actually reachable. So we'll distance ourselves a little bit from even ES trees. And our goal will only be to maintain a spanning forest. We will also relax the notion of ranks to be increasing, but not necessarily of increments of 1. And we see also that in our case, ranks are will mostly be used for optimizations. So here is an example of a valid kind of rank structure in our algorithm. And we can see that along the spanning forest, all nodes are increasing, but not necessarily of increments of 1. So now we have all the background knowledge to kind of see a little bit what our new algorithm is. So our goal here is we have this reference graph, and we want to maintain the spanning forest over the over these operations. So the addition of an edge, the removal of an edge that is either inside or outside the spanning forest. And 2 of those operations are really easy to do, and 1 of them is really hard. So maybe you can already guess which one is which. So we'll start with the addition of an edge. So let's start, let's say we want to add an edge between those 2 nodes here. What we can do is simply add an edge that is not part of the spanning tree, and doing so just works. So we don't need to do additional work, and the reference is thus added, and it's still a spanning tree. If we remove an edge, let's say we remove an edge that is not part of the spanning tree here, again, we can simply just remove it, and it's going to still be a spanning forest. The hard part is if we remove an edge that is part of the spanning tree. So let's say we want to remove the edge that is here. If we do it, we will use a 3-part algorithm that can, we will use a 3-part algorithm to fix the spanning forest. So the first step is to drop, is a drop phase. So the drop phase is a bit the phase that tries to mitigate how much damage we get from removing this edge. And what we will do, we will start from the initial, we will start from the node that is pointed by the edge that we remove. And we will do a BFS from there to mark all those nodes as falling. Okay? And at the same time, we will mark all nodes from these falling nodes, all co-parents from these falling nodes as anchors. So I'll play a little animation, and you'll see this ongoing. So here we have done the drop phase. We have marked all nodes as falling. And at the same time, we have marked 2 anchors. And we will see that the anchors play an important role later on to actually rebuild the spanning forest. So now we can move to the catch phase. So in the catch phase, we will start from the anchors, and we will try to fix the spanning forest and mark all falling nodes that we can still reach. So all nodes that are still reachable. And I think I'll just play the animation. It a bit explain itself. So here, as we can see, we can find all nodes that are still reachable from these anchors. And this way we can know which falling node is still reachable from roots. And as a last step, we will perform the collection of all nodes that are still falling. So here we will simply collect the node on top. And as we can see, this is still a spanning forest. So now the question is, can we use this in practice as such? And as some of you may already see, we cannot use it like this. And the reason is it's about 3 orders of magnitude slower than our baseline, because it's super slow to perform all of these operations on each modification of the heap. And a bit of an intuition behind it is we're tracing pretty much every time a pointer gets modified. So the question is, how can we make it faster? So we have a couple of optimizations. So the first one is called adoption. So an adoption can prevent a node, it's done during the drop phase and can prevent a node from falling if it has a co-parent that has a smaller rank than itself. So again, this is the same graph as we had before, and I'll just play the animation. And as you can see here, this node is about to fall, and this node here is a co-parent with a smaller rank than itself. So we know that we can just modify the spanning tree in place and kind of catch it early on. In this case, it didn't save a lot of nodes from falling, but we could imagine that the 3 dots here are a big subgraph that we would have needed to mark in the falling phase, but now it was prevented by the adoption. And we also know that we cannot form a cycle by doing so because of our rank invariant, so that ranks are always increasing. The second optimization is called re-ranking. So in our case here, we have a new graph. So imagine that the 3 dots here are again a huge subgraph that we really, really don't want to traverse. And the edge in red here is the edge that we want to remove. So if we try to drop this node, we really, really wish that this node here had just a rank a little bit smaller. The reason being that it could adopt it and don't have to traverse the big subgraph. So what we can actually do is just reduce the rank of a potential co-parent so that we don't need to traverse this subgraph. So this is what we will do. We will modify the rank of the nodes here in blue so that this co-parent can now adopt the new, the falling node. And doing so, we can modify in place the spanning tree again to create a valid spanning tree. However, this optimization is a little bit risky because we need to traverse parents going up. And we need to we can only stop if we find a route or we remove enough gaps between the edges to actually increase the co-parent enough. Another scenario that can happen is when we go up, we can actually traverse back to a falling node, and if this happens, we know that we cannot use this co-parent as a valid adopter. And because of this kind of risky move, we only perform re-ranking on the first few nodes each time we do a drop. The third optimization is the choice of the initial rank. So when creating a new object, we can choose its rank. So for example, here we created a new node and we chose to give it a rank of 0. So in our case, we initialize rank with a decreasing global counter. And the reason is that when we create a new object this way, we know that this new node can adopt every node that already exists in the graph. So if we create a bottom-down structure, we can simply add new node really easily without having to do extra work. So as you probably know, the devil lies in the details. There's a few things that we didn't mention about implementation, such as how do we keep the co-parent co-child relationship in memory while we perform all of these operations. So the answer lies in this picture here. We actually embed the co-parent co-child relationship as a linked list, and we use kind of a clever trick, if I can say so, to not have to use any additional external memory allocation. So everything is done as metadata that is added to our object. And also, as you can see, the cost of using our garbage collector algorithm is 2 times of the object plus 4. And there is a whole section about implementation in the paper if you're interested into how we actually implement this algorithm and keep all of this information about parents and co-parents. Now we can talk about benchmarks. So we used Ribbit as our benchmark, which is a scheme implementation. Ribbit is a little bit a torture test for this garbage collector, because almost all operations in Ribbit are memory operations. For example, in Ribbit, the stack is a linked list, so it's very costly to do operations. Ribbit support multiple garbage collectors. So in this case, we compared it against the mark and sweep implementation of the garbage collector. So here are the benchmarks. On the y-axis, we can see the execution time in contrast with the mark and sweep implementation. And on the x-axis, we can see all the different benchmarks used. So we see that we have about a 4.5 times slowdown compared to mark and sweep, which is impressive. Impressive, I don't know, which is better than previous work. So what is the future work? There's a couple directions that we can go from here. One direction is to have more optimization to make this algorithm faster. So for example, using better heuristics. Another idea is to use language information, such as we know that certain structures cannot contain cyclic references, so we don't need to actually use all of this logic, and we could use a reference counter, for example, for part of the reference graph. Another direction could be to implement it in real-world scenarios, such as interoperability with C++ or ROS destructors. And finally, another direction could be to look at other dynamic tree structures in dynamic graphs to see if there is other structures that can be applied to the garbage collection problem. So in conclusion, the arborescent garbage collector collects cyclic structures immediately by embedding a spanning for us into the reference graph. We add a weak notion of rank on objects, allowing the adoption and re-rank optimization. Our technique is about 4.5 slower compared to the mark and sweep implementation, where previous work was prohibitive and unusable synchronously. And we believe that immediate collection of all garbage can enable application requiring timely reclamation of resources. So thank you very much. And
oh, we have maybe more questions than minutes. So maybe if we start at the back and come forwards again.
Yeah, thanks a lot for a very interesting talk and paper. So question I have is, yeah, it's slower, but can you give a breakdown or intuition where is this time spent? As in, like, you have many different, kind of, let's say, paths in your algorithm. Can you kind of tell us which part takes the most wall time?
yeah, it's a really good question. Actually, I have a hidden slide on this. So if we look at the backup slides here, we have another graph that shows a little bit where time is spent on each kind of phase of the algorithm. So we can see that in most benchmarks, it's pretty evenly distributed for the first three, but there's a few ones where we have kind of outsiders. And for the Boyer one, we believe that it's because when we collect garbage, we actually have to remove all co-friends, and in this case, there's a lot of co-friends, and yeah. So anyway, that's it.
Thank you. Did you consider parallel mutators, and also did you consider batching?
Sorry, can you repeat?
did you consider parallel mutators, and also did you consider batching of this processing, addition and removals?
Yeah, we didn't consider parallel implementations, and I don't see a straightforward way to implement it in a parallel way. There probably is, but it would be a future work. Yeah.
Okay, maybe there's the last question.
Yeah, so you said there was previous work that was a lot worse, but can you say a few words about what it is, and is it yours? I don't know. And just a simple, a short question also. The Evan-Shiloach tree, it was minimal in something, and you were not. In what was it minimal?
Okay, so when I talk about previous work is that the previous work that exists was too prohibitive to be used synchronously. They had to use other, use it in a asynchronous fashion, because otherwise you would traverse your heap multiple times during the execution of the program. I actually also have a backup slide a little bit on the previous work here. And your other question about ES trees. So ES trees is a construct in dynamic graph theory, and its goal is only to keep the minimal distance at each moment from given roots. So its goal is not garbage collection. Its goal is really just to know the minimal distance from roots. But in the case of garbage collection, we actually don't need this information, so we can relax this notion of distance, let's say.
Okay, well, I think we need to take the coffee break now, but I'm sure you'll be here during the break and able to maybe expand on any remaining questions that people have.
Yeah, for sure. I'll stay here if you have questions.
Great. Well, let's thank the speaker again.
Thank you very much.
Yeah, I think we're resuming after the break at 3:40.
Having tried to implement something like this during an internship, I have an
now with a talk on fully randomized pointers by Sai Dewal-Pai, Gregory Dirk, Roland Yap, Trevor Carlson from the National University of Singapore. Thank you, Sai.
Thank you very much, Steve. All right. Good afternoon, everyone. My name is Sai, and I'll be presenting fully randomized pointers, which is a joint work with my colleagues at National University of Singapore. For decades, memory errors have been the Achilles heel of software written in C and C++. In this talk, I'm going to talk about fully randomized pointers, or FRP, which is a memory error defense that for the first time provides strong capability-like security while remaining compatible with existing unmodified binary software. Let's start with the fundamentals. At its core, memory errors occur when a program tries to access an object or memory outside its intended reference. There are two kinds, I'm sure you're all familiar with: out-of-bounds errors and use-after-free errors. The problem is not new, but these memory errors are incredibly persistent and pervasive. As you can see from industry reports, on the left, Chromium shows that out of the high severity bugs that they patch, about 70% of them are memory bugs, out of which a very significant portion is use-after-free bugs. And on the right, you can see a report from Microsoft Security that shows a staggering 70% of the bugs that they patch have their root causes in memory safety. It's not a small number. They are the primary cause of vulnerabilities being discovered and patched today. And they're not just abstract. These vulnerabilities lead to real-world security disasters that many of us will recognize. From the infamous Heartbleed bug of 2014 that exposed sensitive data across millions of servers due to an out-of-bounds read, to the recent pseudo-heap overflow vulnerability that allowed for local privilege escalation in practically any Linux server that was having the problem. More recent examples show that memory errors pervade in cloud infrastructure as well as the V8 engine that powers our browsers. Each of these incidents was rooted in a fundamental memory error, demonstrating the urgent need for an effective solution. Now, let's look at the anatomy of an exploit. What makes an attacker turn a simple bug into a full-blown exploit? Well, the attacker needs a few capabilities. The first of which is they need to be able to craft invalid pointers, either out of bounds or dangling. They need to be able to dereference these pointers. And they need to leverage the program's memory layout to know where to read or write data or find control structures or put sensitive data. The Heartbleed exploit is a classic example. An attacker sends a malicious request which causes the buffer to allocate more memory than it was intended to, and it reads memory into a buffer, copies it to a response buffer, and sends back to the attacker. It could be passwords, it could be garbled data too, to be honest. However, this is a typical exploit. We have to consider the adversarial strong attacker, a real world attacker, who has all the capabilities that we talked about with one crucial addition: the ability to retry attacks. Specifically, retry without triggering any interventions. A real world attacker will not give up. They can try again, perhaps with different inputs. This ability to brute force or systematically search for vulnerabilities fundamentally changes the security landscape, and it challenges many defenses. The power of retry attacks is not just theoretical. Network servers are often configured to maintain high availability, and that's why they restart after a crash, giving an attacker a new attack attempt. Speculative execution attacks in practicality allow invisible number of retries without crashing. And then there is a technique of heap spraying where an attacker creates many objects, hoping that one of them will land on the targeted object. The point is, retrying enables strong attackers to systematically brute force defenses. There have been a certain class of defenses called entropy-based defense that have tried to solve this issue. In entropy, they use randomness. The defense uses randomness. The attacker needs to essentially guess a randomized tag. Incorrect guesses should cause a crash. Pointer tagging uses the upper bits in a pointer, for example, in heap check, to store a tag. Pointer authentication, on the other hand, stores a machine authentication code, a message authentication code, And then there are techniques such as pointer encryption, which partially encrypt pointer values. The core idea is the same. An attacker needs to guess the random value to forge a valid pointer. And I'm sure it's pretty evident what parts are tagged. However, there's a limitation. The best of these defenses top out at 24 bits of randomness, which is very, very easily bypassed. 24 bits is not strong, not strong enough to stop a determined attacker. To give you an example, a Pacman paper showed that speculative execution is possible to test values at a high rate. At this rate, 16-bit entropy can be brute forced in under 3 minutes. And extrapolating this, 24-bit entropy can be brute forced in under 12.5 hours. This is well within the means and the capabilities of a patient attacker. Low entropy combined with the power of retries makes a defense practically bypassable. So if this is the limitation, what is the solution? If low entropy is the problem, the solution is much higher entropy. That brings us to our contribution, fully randomized pointers. It's a new pointer encoding to maximize randomization of pointer bits without breaking binary compatibility. To put this in an example, on the left you can see a typical ASLR heap randomized objects, P and Q subsequently allocated. You can see if an attacker has an information about P, they can very well reach Q. On a fully randomized pointer setup, P and Q are essentially large random numbers. Having an information about P does not give an attacker any information about Q, making it impossible to forge. To do this, we had to rethink pointers. Well, what is a pointer? A pointer is just a handle that points to an object in memory. There are a few core requirements that a pointer needs to fulfill. It should support dereference, it should support pointer arithmetic, and it should be packed in a 64-bit machine word. But the core insight is pointers need not be machine addresses. They are just one possible encoding. And most binary software works out of the box without recompilation as long as the core pointer requirements are met. So how do we design an FRP? We start by abstracting a pointer into a pair, a unique object identifier, and a byte offset within the object. For security, we fully randomize these components. When an object is allocated, it's given a new 40-bit ID. We also randomize the offset separately. Finally, we pack this into a 64-bit machine word for compatibility. The result is a pointer that looks like a regular pointer to the program, but is actually a securely randomized abstract handle. On the right, you can see an example. We start with the traditional pointer, which abstracts into the ID offset pair 1, 0. Both components are randomized, and then we pack it into a 64-bit word. However, FRP still needs to allow operations of the core requirements of a pointer. How does FRP do the low-level operations? On the allocation, a new entry is added to a map, which is fairly trivial. We add the ID of the object, base of the object, size of the object, and a packed FRP is returned to the program. Pointer arithmetic is straightforward. We just need to add or adjust the offset part of the pointer. The ID remains unchanged. This preserves object identity across pointer arithmetic operations. As for pointer dereference, when a pointer is dereferenced, the system first looks up an ID in the map. If the ID is missing, we detect use after free. Then we perform a bounds check. And if any out of bounds accesses are caught, we raise an error. If both of these checks pass, only then do we allow the dereference to proceed as normally. On the right, you can see an example. The top is an example of a map entry. Then we are performing a pointer arithmetic operation, which is taking forward as it should in a regular program. The blue fat part shows the interception of our technique, which decodes into the base address, and finally does a bounce check. After passing, a traditional dereference takes place. This approach ensures that every pointer operation is both compatible and protected with minimal disruption to the program logic. Now let's see what is the security impact of such a technique. We achieve a baseline security of 52 bits of entropy, which is an astronomical leap from the 24 bits in prior approaches. The high entropy provides robust protection against both use after free and out of bounds errors. An attacker would need to guess a 52-bit random value to attack a pointer Q, having an information about P. Just how hard is it to brute force 52 bits? Let's put it into perspective using the examples that we saw before. For the network server reset example, 52 bits of entropy, an attacker would require 2 to the 51 guesses for one attack. The TCP handshake traffic itself would exceed 240 petabytes, making it intractable. For the speculative execution attack, using the same optimistic rate, for an FRP space, it'll take 384,000 years, which is far exceeding the 24-bit defense. Even a massive heap spray that allocates billions of objects barely makes a dent. The FRP space is so vastly larger than physical memory that the probability of a successful attack is negligible. With 52 bits of entropy, brute force attacks are no longer a viable threat. To prove the practicality of our design, we built 2 prototypes. BlueFat, which is a software prototype built on Intel Pin Dynamic Binary Instrumentation Framework that is used to test security and compatibility. We also developed GreenFat, which is a hardware simulation built on the Gem 5 simulator. The purpose was to evaluate performance. Looking at BlueFat, our security evaluation shows that FRP prevails where others fail. On the right, you can see a table. The top represents CVEs ranging from weak to strong, including the strong attacker model that we discussed before, with the ability to write retry attacks. We tested a bunch of defenses on them, and you can see FRP is the only one that's completely bypass safe or doesn't fail in the attacks. Even more importantly, BlueFat successfully runs the entire Spec 2017 suite, which comprises of C, C++, and even Fortran binaries without any recompilation. This validates our core hypothesis that FRP's novel pointer encoding is highly compatible with real-world off-the-shelf binary software. Well, security and compatibility are good, but not at the cost of performance overheads. This is where GreenFat comes in. We simulated a hardware accelerated design and added a small dedicated GreenFat cache to the processor core. This cache stores FRP to address mappings, and we decode translations on the fly. This only adds a cache hit latency of 2 cycles. The results are excellent. We get less than 4% geomean performance overhead when testing on Spec CPU 2006. This is well within the acceptable range for an always-on security feature in production systems. In conclusion, we have shown that it is possible to fundamentally redefine pointers away from machine addresses to achieve a new level of security. Fully randomized pointers offer 3 benefits: an unprecedented baseline 52-bit entropy with high binary compatibility and practical performance overheads for production systems. FRP demonstrates a new superior trade-off point that strong bypass safety and binary compatibility can coexist together. We have open sourced BlueFat on GitHub for you to explore. And for more details, you can check out the paper. Thank you for your attention. I'd be happy to take any questions.
Thanks for the great talk. Yes.
Thanks, very nice work. People often do things with pointers that are kind of outside the C spec. So some things, we work with Cherry, which is kind of similar to what you do. And some things I think you can support that we don't. So sometimes people hide pointers just by knotting the bit pattern. And I think that would work with your thing perhaps, wouldn't it? Sorry, rest of the question. And other times people XOR pointers. And I don't think that would work with your thing, would it?
You're right about some techniques that use, for example, NAND boxing in Chrome or SpiderMonkey, or where the pointer bits are otherwise used, will be incompatible with FRP. But that represents a small part of the software stack as well, in terms of compatibility, right?
Martin Maas, Google DeepMind. Really nice talk. Really enjoyed the work. Building on that question. So there's some of the uses of these high bits are, for example, for distinguishing kernel pointers from user mode pointers. And then, of course, there's also canonical addresses versus malformed addresses. And so it seems like currently this is assuming all of that is randomized, but could you imagine extending your work so that it becomes configurable? So for example, that you could require all of the random addresses to be canonical addresses?
Well, that is a good direction to think about. Even in our example, the ID and offset parts, as you saw, they are configurable. You can change the part that stores the ID as well as the part that stores the offset. This is practically done to avoid large objects, which currently only supports, you understand, only the 6 down bits, bottom bits. We can extend that to be a configurable system. This is just the baseline example, but yeah, that's a good direction I can think about.
So on the same topic at the end, how are you distinguishing which part's offset and which part's ID? Like, is that variable or is it fixed? And does that limit the number of objects and the size of objects?
You can configure before the start or before the running of, before you run the program. So it's static once you start it. So you can decide how many bits will represent offset or how many bits will represent ID, but it's not variable while running the program for sure.
Have you considered encoding a size class in there to give you a variety of splits between offset and base?
We have not, but thank you for the feedback.
One more question.
So some programming languages, including C, can use garbage collected system, and some garbage collection algorithm will have this kind of operation. They will linearly scan through a range of memory and go from address one by one and find places where existing object is allocated. But because if pointers are randomized, is it still possible to do this kind of linear scanning? Okay.
I mean, it could be possible, but then GC would have to not pass through the randomized setup, because as we see, the memory layout is not randomized. The memory is still getting allocated contiguously. It's only the abstract handle on the virtual side of it that is getting randomized. So GC can work with physical addresses. Maybe that's a solution.
All right, let's thank the speaker.
Thank you very much.
Our next speaker is Satvik Swaminathan from Intel Labs. And he's going to be talking about tier train, proactive memory tiering for CPU-based DNN training.
So we'll be going over the motivation for why we want to do this and some necessary background, and we'll be looking at... Is it working now? Yeah, and we'll be looking at the core of the work, which is tier train, and some results. So why is using DRAM not enough for DNN training applications? Well, on a general note, in most data centers, DRAM accounts for about 50% of the overall cost. So it's getting more and more expensive. And we also noticed that in a report from VMware, it costs around 90% of the overall cost, which is around 50% of the total TCO. So we can see that the cost of DRAM keeps going up, and as your workloads become bigger and bigger, this issue is only going to get more worse. So why do we want to use this for deep learning models? Is because as the model size goes up, we are going to access a lot more weight parameters, and then the memory requirements also shoot up. So we will require more DRAM to run these models. And soon, compute is no longer going to be an issue. It's memory that's going to become an issue. And so we have this popular memory wall problem that we come across. And we are looking at memory tiering as a solution to address this memory wall problem. So this is just some background on memory tiering. So in a typical memory tiering system, we have multiple tiers of memory, meaning on different levels, we will have different memory technologies which have very different characteristics. So for example, in your typical system, we have a cache which has a very low capacity, but it has a very high bandwidth, and the latency to it is very small. So similar to the cache, we also have something called high bandwidth memory, which is very prevalent on GPUs. And so these are hop memory tiers, meaning that we would want to place data that is being accessed very frequently on these tiers. And on the other end, we have cold memory tiers, something like CXL attached memory or Intel Optane, which supports a very large capacity, but then the latency is very high and the bandwidth is very low. So we would just use this as a capacity tier where we would want to place data that's infrequently accessed. And coming to the key observation that we have made, which we'll exploit later on, is that, so on the right, we have the address space which shows the memory access pattern when we run a DNN training workload. So what happens when the forward pass runs is that, so every dot in this particular image refers to a single page being accessed. So during the forward pass of the first epoch, of a single epoch, what happens is a bunch of pages get accessed in this fashion. And during a backward pass, what happens is these pages get accessed again. So basically, a lot of tensors are being produced in your forward pass, which are again being accessed in the backward pass. And the same thing happens in the second epoch too. So there are tensors. So DNN has multiple layers, and each of these layers, they produce a lot of tensors. So these are referred to as safe tensors, which are basically intermediate tensors, which is written to in the forward pass, and it's again being read in the backward pass. So we notice that there are some tensors that are being produced by every layer in your forward pass, and it's going to get accessed in the backward pass, but it's going to happen in the reverse order because gradient descent runs in the reverse order. So for example, a tensor that's being produced in the first layer in the beginning of the forward pass, in the beginning of the epoch, gets accessed only again during the end of the first epoch because the backward pass of the first layer runs towards the end. So there is a lot of idle time, and idle time basically refers to the period of time for which these tensors don't get accessed. So the idle time for, say, these tensors corresponding to the first layer is very huge, which means it does not get access for a long time. Whereas if we look at the final layer of our network, it gets accessed immediately after, leaving it zero idle time. And the same pattern is observed across different epochs. So TATrain is going to try and exploit this fact because there's a lot of time over here for which is not being accessed. So we don't have to store all of these tensors in some fast, expensive memory like DRAM. Instead, we can offload it to a different medium. So this is what TATrain roughly does. So in frameworks like PyTorch, we basically have hooks which can provide us information on all of these tensors, including their size, their address, and the timing information of all of these layers. So we get this information and then we pass it to TATrain, which is basically a daemon running in the background. And then TATrain knows when a layer is going to finish. So once a layer is going to finish in the forward pass, what happens is whatever saved tensors has been produced can now be migrated to a different memory tier, which is not as expensive. And the amount of data it wants to migrate depends on how much memory bandwidth is available on the system and other factors. So this basically is being migrated. And again, we want this data to be prefetched back in time before the same layer in the backward pass accesses those tensors again. So it's going to decide whether to prefetch this tensor or not, depending on whether it has been migrated in the first place. And if it has to prefetch, it's going to prefetch how much ever data it evicted back to your fast tier, so that we don't have to face the consequences of the workload accessing this data from the cold tier, which would lead to a lot of performance loss. So we have a simple queuing system which takes care of when and how much data to evict during the forward pass. So we basically get the duration of a layer, the size of all of these tensors from the hooks, and then we trigger eviction right after a particular layer gets evicted during the forward pass. And like I said, the size of this eviction depends on how much memory bandwidth we have available, and what is the idle time for these tensors. So for example, if we look at layer number 3, then it's going to be accessed immediately after. So we decide not to evict these tensors at all. It's going to be present in DRAM at all times. And all of these tensors get accessed in the reverse order during the backward pass. So the prefetch has to be triggered at the right amount of time so that it gets prefetched before these tensors are accessed again. So we don't want to prefetch these tensors too early, because if we prefetch them too early, then it's going to occupy more of the fast memory for no reason. And we don't want them to prefetch them too late either, because that would lead to a performance loss. So we have these equations running in the background which determine when exactly we want to trigger a prefetch. And now we can look at some results of tier train. So initially we did an evaluation on real CXL attached memory, and so these are the results we observed. We have around 2 terabytes of DRAM on the system and about 256 GB of CXL, and we have tested tier train across different variations of ResNet on CXL, and so we can notice that on an average the DRAM reduction is about 48 to 59% with the baseline being execution in pure DRAM. So the highlighted line here is the pure DRAM number, and then there's very minimal performance impact because most of the data is being prefetched back in time. So there's about 1 to 5% performance impact. And we have also done the same evaluation on a system that has both DRAM and Optane. So there is 768 GB of DRAM and 4.5 terabytes of Optane being supported on the system. And we compare this against other tiering tools such as MEMTLD and HEMEM. And the baseline here is again pure DRAM execution. And so compared to all of these methods, there is again an average DRAM reduction of 59 to 83%. There's a peak DRAM reduction of 25 to 74%. And this has been tested across various benchmarks like your transformer models and a lot of graph neural networks and a lot of CNNs like ResNets. And we also want to see what would happen if the available DRAM on a system is not enough to support the overall footprint of the application. So for this example, we have chosen ResNet 152, whose footprint is 150 GB. And we only have 60 GB of DRAM supported on the system and about 1.1 terabytes of Optane. And then we compare this against Autonoma, which is a tiering policy that is supported by Linux, and MEMTLD, and our baseline is again pure DRAM. And we notice that, so what happens in this case is, once the DRAM runs out, most of the data is going to spill out into Optane in the baseline. So that's going to lead to a lot of performance degradation, takes around 2000 seconds. And MEMTLD and Autonoma and tier train in the background, they try to reshuffle this data across different tiers. And we notice that tier train outperforms MEMTLD, HEMEM, and Autonoma by 35, 37, and 84% respectively. And one reason for this is that all of these tools, they are not tailored for DNN training's memory access patterns. So it is a very, very reactive way to tiering data, as in it first detects that some data is being accessed and it realizes that it's hot, and then it moves it to a hot tier. But by the time the data might have already been accessed, so it might be too late. So tier train does it in a proactive fashion where it receives all of this data from the hooks, and it knows exactly when to prefetch and evict all these tensors. So in conclusion, all the existing solutions, they are inaccurate and they are slow in the sense that they might not be able to prefetch all of this data in time once the data has been detected to be hot. And tier train addresses these challenges by understanding the DNN training workflow pattern. So basically we have the first epoch, which is sort of a profile epoch where it gets all this information, and then it starts tiering data from the second epoch onwards. And yes, it does this in a proactive fashion where it doesn't have to wait for the data to be accessed. It just prefetches all the tensors in advance. Thank you.
We have time for some questions.
Hello, I'm Singhan Nam from Seoul National University, and actually your work looks awesome because from the performance and the RAM reduction. But in real world, as far as I know, most of the training are done using GPU or accelerators. Then, could you apply the same tactic for GPU and accelerator-based training, or could there be some peculiarities that prevent them from being easily applied?
So the technique prescribed here is agnostic. It can run on GPUs as well as any accelerators that support data movement. So here we did it on CPUs because, so basically the implementation alone is CPU specific. It can very well be done on GPUs. You just have to change the implementation and use the according calls for performing the data migration, but it can be performed on GPUs, yes.
Thank you for the great talk, Tomoharu Gawa, University of Tokyo. And my question is related to the previous question. So if you use a GPU, is the boundaries between the slow memory and the fast memory sufficient? So, if the bus between the slow and high memory is slow, it is we cannot prefetch enough data.
So in this case, tier train runs as a daemon. So all the migration is being done in the background while your DNN training application runs. So if I'm using a GPU, for example, all the transfers will have to happen across the PCI bus. Say if I'm trying to transfer it between CPU memory and GPU memory. So we'll just have to ensure that the prefetch is triggered at such a point in time that we are able to migrate the data in time to the GPU memory so that you won't have any accesses going across the PCI bus. And tier train also makes sure, for example, let's say you have a lot of data to transfer in very little time because sometimes the idle time of these tensors is very small, especially for layers towards TN. So tier train automatically calculates how much data can you migrate given that the idle time is only so much. So sometimes it chooses not to migrate the entire tensor, and it only migrates a partial tensor.
Martin Mask, Google DeepMind. Really nice talk. So an alternative to keeping the data in memory is to rematerialize or recompute tensors. Have you looked at how your technique interacts with those approaches?
Could you come again? Which ones?
So instead of keeping the forward, like all the data from the forward pass in memory, you can drop some of it and then rematerialize it during the backwards pass. How does it interact with your technique?
We could recompute it, yes. So if we want to recompute, then there would be no memory tiering to perform because these sensors won't be present in memory. But then the memory requirements would be, if we recompute it, yes, the memory requirements would come down. That is not something we have looked at because the training by itself takes a lot of time. So in order to recompute it, the training time would be very high. So that's not something we have looked at yet.
Thanks.
We have time for another question if someone would like to ask one. Yes.
Hello, Jeremy Singer, University of Glasgow. I think your technique is very nice for repeated traversals of regions of memory. How complex can those traversal patterns be? The one you showed us was just kind of all the way down and all the way up. I'm thinking of maybe more complex traversals that kind of went over perhaps dynamic data structures that are very large or something like that, would your technique be able to do prefetching for those kinds of things as well?
Right now, the technique is pretty tailored for the memory access patterns that we have observed. But if the daemon is fed with the right data, as in, say, if these iterations are occurring multiple times, and in the first iteration, the daemon knows, just gets a sample data as to when it has to prefetch and when it has to evict, then it is going to use that same data to perform the evictions and the prefetches in the upcoming iterations. Coming to this pattern across a lot of models, we have observed the same pattern at least for DNA training applications, because this is fundamental to gradient descent. But in case of more complex models where the network itself might change structure during training, I'm not sure if that happens. But if that happens, yes, this will slightly change. But what will matter more is the data that's being communicated between the DNA training workload and the daemon. So as long as that data is being fed in a format we expect it to be fed, then this would still work.
All right, thank you.
Thank you very much.
Thank the speaker. So our next two talks, as many of you know, visas can be a problem when we're traveling to conferences, and unfortunately our next two talks, the speakers are not here in person, but we have pre-recorded talks, and with a bit of luck, we'll have both speakers respectively on Discord to respond to questions via an audio connection at the end. So what we're going to do now is watch a pre-recorded talk, and at the end, you should still be able to have a Q&A for this talk via an audio link. So without further ado, let me introduce the next talk. It will be EMD, Fair and Efficient Dynamic Memory Debloating of Transparent Huge Pages. And the authors are Parth Gangar, Ashish Panwar, and K. Gopinath. And they're from Fujitsu Research, Microsoft Research, and Rishihood University in India, respectively.
Hello everyone, I am Parth Gangar, and today I'll be discussing my work on efficient memory debloating, or EMD, a system. Hello everyone, I am Parth Gangar, and today I'll be discussing my work on efficient memory debloating, or EMD, a system designed for fair and efficient dynamic memory debloating of transparent huge pages. Now this slide outlines the structure of my presentation. I'll start with a brief introduction to virtual memory and huge pages. Next, I'll discuss the motivation, specifically focusing on the need for fair and efficient dynamic memory debloating in operating systems. Following that, I'll delve into the design of our proposed solution EMD. We'll then move on to the evaluation phase, where I'll present results that demonstrate how EMD improves fairness and efficiency compared to existing solutions. Finally, I'll conclude with some closing remarks. Now, virtual memory is essential in modern computing, where the software accesses memory through virtual addresses that must be translated into physical addresses. As memory demands surge with big data workloads, physical memory has expanded from a few megabytes to gigabytes and now to terabytes. Now, these workloads require fast access to vast amounts of memory, making efficient address translation crucial for efficient memory access and overall computing performance. To accelerate this virtual to physical address translation, processors cache recently used addresses in multi-level hardware structures called translation look-aside buffers, TLBs. A miss in the TLB can take several memory accesses and may incur hundreds of cycles to service. As memory capacity grows, deeper page tables add another level of memory access, further increasing the cost of a miss. Now, in a virtualized environment, a TLB miss may require up to 24 memory accesses. Unfortunately, while physical memory capacity has grown exponentially, the size of the TLB has barely scaled over the decades. Now, increased memory consumption, deeper page tables, and limited TLB growth, they lead to a phenomena known as the address translation wall, where the memory management unit spends a significant number of cycles translating virtual addresses to physical addresses. Now here is a graph showing percentage of CPU cycles spent in page table walks by various Google data center workloads. As you can see, 9 to 38% of total CPU cycles are dedicated to page table walks alone. To mitigate the cost of virtual to physical address translation, modern processors support huge pages. A huge page enables the hardware to map a much larger fraction of virtual address space into physical memory via a single TLB entry. Huge pages increases TLB coverage, which in turn reduces the frequency of TLB misses. Here is a graph showing the performance benefits of huge pages over base pages. For all these workloads, we observe at least a 60% performance improvement over using base pages. An important note is that in this context, we are discussing transparent huge pages, a technique where the operating system automatically allocates huge pages without user intervention or application level code changes. In Linux, this mechanism is known as Linux THP. Now, while huge pages improve performance, they introduce new memory management challenges. Here are the main issues many workloads encounter when using transparent huge pages, although several research efforts have addressed these challenges. Memory bloat remains a significant problem that no prior work has fully solved. Our work specifically tackles this issue, aiming to effectively eliminate memory bloat. Now, this is the graph we saw earlier showing the performance benefits of huge pages for these workloads. Now, below is a table that illustrates the memory overhead associated with using huge pages. As you can see, for all these workloads, the use of huge pages increases the memory footprint. Now, these observations highlight an important trade-off. Performance can be optimized at the expense of extra memory. Ideally, this trade-off should be effectively managed by the operating system. However, we find that current systems either lack support for managing memory bloat or are not efficient at it. Next, we'll discuss what is memory bloat and what is debloating. Now, memory bloat occurs when an application uses more physical memory than necessary due to the allocation of huge pages. For example, if an application accesses just 1 byte of virtual memory, allocating it with a 2 MB huge page results in more memory waste compared to a 4 KB page. Now, this waste occurs because with sparse access patterns, the entire huge page often remains unused, leading to unnecessary memory bloat. Now, Linux THP primarily supports huge pages for anonymous memory mappings, which the kernel initially zero fills. Now, this is an important characteristic which allows for automatic recovery of memory bloat under pressure. Now, debloating is the process of reclaiming these zero-filled pages from a process. During debloating, the huge page is broken down into its constituent base pages, and the zero-filled base pages are deduplicated into a single zero-filled physical memory page. Now, next, we will see how existing systems deal with memory bloat. Linux is both greedy and aggressive in its memory management. It employs a first touch policy for huge page allocation, where physical huge pages are allocated upon the first page fault. While this approach helps reduce TLP misses, it does so at the cost of reserving entire regions of memory for processes that may use less than a full huge page, leading to memory bloat. Now, Engines is a work in OSDI 2016 which promotes huge pages asynchronously using conservative utilization threshold parameter for huge page allocation to prevent memory bloat. Now, FreeBSD is an operating system used in many modern servers, desktops, and embedded platforms. FreeBSD supports transparent huge pages using reservation-based huge page allocation. Now, Engines and FreeBSD huge pages are only promoted after a certain threshold number of base pages have been used. Now, thus, these strategies help prevent memory bloat, but result in an increased number of TLB misses. Hawkeye, which is a research work in ASPLOS 2019, promotes huge pages on the first page fault. It introduces a dynamic memory debloating mechanism under memory pressure to balance the trade-off between memory efficiency and performance. Next, we will see why Hawkeye is suboptimal and unfair. To illustrate why Hawkeye is suboptimal, we performed an experiment with a synthetic micro benchmark that demonstrates uneven memory bloat. The graph on this slide shows that memory bloat is low in the first half of the address space and high in the second half. Now we used Hawkeye to debloat 25% of the memory and compared its performance to a no debloating scenario. By debloating 25%, we mean that if an application uses 8 GB of memory, we reclaim 2 GB of zero-filled pages. We found that Hawkeye resulted in a 74% slowdown compared to no debloating. Hawkeye addresses memory bloat by scanning the address space sequentially and breaking huge pages if they contain zero-filled pages. However, this approach is not very efficient because it overlooks the crucial fact that memory bloat is different in different parts of the address space. In our experiment, Hawkeye had to break 2/3 of the total allocated huge pages to reduce memory bloat, leading to a situation where there are more base pages than huge pages. As a result, the performance benefits of huge pages are negated. To demonstrate the lack of fairness in Hawkeye, we ran two identical instances of the B-tree workload simultaneously and compared their performance under Hawkeye. We conducted the same experiment with Memcached as well. To distinguish between different instances of the same workload, we labeled them according to their process creation order. For example, instance 1 represents the first instance 2 represents the second instance of the same workload. As shown in the table, Hawkeye's unfair reclamation policy disproportionately affects the instances. For B-tree, Hawkeye breaks over 19,000 huge pages in instance 1, but only 1,300 in instance 2, a 14.6x difference. Similarly, for Memcached, the difference is 4.7x. Now, this imbalance occurs because Hawkeye debloats memory from another instance only after fully debloating the current one, leading to uneven performance impacts. For B-tree, instance 1 experiences a 28% slowdown compared to no debloating, while instance 2 sees only a 2% slowdown. For Memcached, the slowdowns are 22% for instance 1 and 4% for instance 2. Now next we'll explain the design of EMD. Now here is the virtual address space of the micro benchmark showing uneven memory bloat distribution. Now this graph, which we saw earlier, represents that uneven distribution. For simplicity, let's divide the address space into 6 huge page candidates labeled H1 to H6. Our approach EMD uses a prioritization scheme for debloating memory regions. Each region is debloated based on a priority value, which is determined by the number of zero-filled base pages within a huge page. The more zero-filled base pages, the higher the priority value. In this setup, H1 to H3, the first half of the address space, have no memory bloat, thus low priority, while H4 to H6, the second half, have high memory bloat, thus high priority. We use a data structure called the bloat map, which is an array of 10 buckets. Now each bucket represents a different priority value and contains huge page regions with the same priority. So H4, H5 and H6 are placed in high priority buckets, while H1, H2 and H3 go into low priority buckets. As a result, EMD debloats the second half of the address space first before moving on to the first half. EMD's fine-grained approach scans each base page within a huge page. For non-zero filled pages, we skip the base page as soon as we detect the first non-zero byte. However, for zero-filled pages, we need to scan the entire base page. Therefore, the scanning overhead depends on the number of zero-filled base pages within each huge page. As shown in the graph, the average overhead remains quite low, which is 0.2%. Now, under multi-tenancy, EMD debloats memory regions from the same priority bucket across all processes before moving on to the next bucket. For instance, consider two processes, A and B, launched immediately one after the other. Now, if both processes have memory regions in the same priority bucket, EMD will debloat all regions in that bucket for both processes before moving on to the next bucket. For example, here A has regions A3 and A5 and B has regions B1 and B6. All of these regions are in the same priority bucket. So EMD will debloat A3, A5, B1 and B6 together before addressing the next priority bucket. Now this approach ensures that regions with the highest bloat are addressed first across all processes, promoting fair memory reclamation. It prevents any single process from being disproportionately affected, thereby achieving a more balanced performance and enhancing overall system efficiency. Thus, the final order of debloating would be B5, A1, A3, B1, A5, B6, B3, B4, A2, A4, B2, A6. Next, we'll move on to the evaluation section. Now, this table outlines the experimental setup used to evaluate our approach. We assessed performance and fairness under three scenarios: single instance workloads, multiple instances of the same workloads, and multiple instances of different workloads. Now, we selected a mix of real-world workloads and custom micro-benchmarks for our evaluation. Now, the figures presented show the bloat distribution across the virtual address space for each of these workloads. For example, B-tree shows no memory bloat for the first 15% of the address space, then experiences a sharp increase to around 90%, which remains consistent for the rest of the address space. Memcached, on the other hand, has memory bloat ranging from 50% to 99% for most of the address space, dropping to 0 towards the end. Random access L and random access R exhibit consisting bloat patterns. Random access L shows low memory bloat in the left half and high bloat in the right half, while random access R has high memory bloat in the left half and low bloat in the right half. We evaluated the impact of debloating on single instance workloads by reclaiming different amounts of memory bloat, such as 20%, 30%, and so on. For example, if an application uses 8 GB of memory and we debloat 20%, we basically reclaim 1.6 GB of zero filled pages. The graph shows the performance impact of Hawkeye, which is in orange, and EMD, which is in green, across 4 workloads: B-tree, Memcached, random access L, and random access R at various debloating levels. We are comparing Hawkeye and EMD against no debloating scenario. Now, as you can see, Hawkeye significantly increases runtime across all debloating levels with an average increase of 1.1x for B-tree and 1.2x for Memcached. In contrast, EMD's fine-grained approach, which considers the bloat distribution across the address space, results in minimal performance impact. For B-tree and Memcached, EMD shows an average runtime increase of less than 1.01x, closely matching the best case runtime. At 50% debloating, both Hawkeye and EMD see increased runtimes for the random access micro benchmarks. Now, this happens because over 75% of huge pages are broken during debloating, causing the application to rely more on base pages, making its runtime similar to native execution time. For random access L, Hawkeye's average runtime overhead reaches 1.84x, while AMD shows a 1.28x increase, reflecting a 56% improvement. Hawkeye and AMD perform optimally for random access R with an average runtime overhead of 1.28x, since the optimal order for debloating in this case is sequential. Now, to understand why EMD outperforms Hawkeye, table shows the number of huge pages broken by both methods at all debloating levels. Hawkeye, which debloats memory in virtual address space order without considering the varying debloat levels, breaks more pages compared to EMD. On average, Hawkeye breaks 6% more huge pages for B-tree, 22% for Memcached, and 41% for random access L. However, the number of huge pages broken by both methods is same for random access R. Thus, EMD outperforms Hawkeye by breaking fewer huge pages and debloating memory in a fine-grained manner, thereby minimizing the performance impact. Now, under multi-tenancy, we execute 4 identical instances of B-tree, launching them one after the other with a few seconds of delay in between. The table shows the number of huge pages broken across all 4 instances of B-tree for various debloating levels. Hawkeye breaks huge pages one instance at a time based on the process arrival order. It starts debloating memory from the first instance and moves on to the next instance only after scanning the address space of the prior one. In contrast, AMD ensures fairness by judiciously breaking huge pages across all instances. It identifies the most bloated regions across all instances and debloats them. For example, in the case of 40% of debloating, Hawkeye breaks 47% of the huge page from instance 1, 44% from instance 2, and 10% from instance 3. It never debloats memory from instance 4. In the same scenario, EMD breaks 27% of huge pages from instance 1, 27% from instance 2, 24% of instance 3, and 23% from instance 4, ensuring fair debloating across all instances. Now, before I wrap up, here are 3 key takeaways from this work. Current systems don't efficiently support dynamic memory debloating. EMD reclaims memory bloat effectively with minimal performance impact. EMD ensures fairness even in multi-process environments. Our system also requires no hardware or application level changes. Thank you.
Parth, can you hear us?
Yeah.
Good.
I can hear you.
Okay. Full screen.
Hello? Hello?
Hi. Sorry, we're just setting up in here.
All right.
Yeah.
Terrific.
Audible?
Yes, terrific. Now, thank you for the talk. I'm the session chair, Steve Blackburn. I'm going to now hand over to questions from the audience.
Sure.
Hi, I'm Tim Harris from OpenAI. I haven't read the paper yet. Thank you for a very nice recording, but maybe this is answered there already. I was wondering what scope there is for taking usage counts into consideration as well as the mapping. So knowing that maybe a huge page has a lot of accesses going through it, even though there's a lot of zeros, and maybe it's best to keep that as a huge page when thinking about the overall performance trade-offs.
Hello. Thank you for the question. Firstly, I just wanted to clarify is that you are saying that the huge page, how is the performance impact when using huge pages? It's better than, let's say, not completely use huge pages. Is that what your question is?
And I was wondering if the reduction in TLB use, if there's a very popular huge page, even if it's inefficient in terms of the amount of non-zero data it contains, is something that's worth retaining.
Yeah. So I have mentioned in the paper. So there is a graph of EM, basically completely not using, only using base pages, and then using EMD with huge pages. So it's like there is a high bloat scenario and there is a low bloat scenario. So you can basically dynamically manage the trade-off. So the difference between completely using base pages and then yeah, let's say using huge pages but with EMD, that performance, there is a performance gain in that as well.
Thank you.
Hi, Eric Aslan from Oracle. I'm wondering if you've considered, rather than debloating after the fact, when the bloating has already occurred, potential heuristics for not introducing the bloating in the first place, so that you don't need to debloat it, and if there could be some strategies there to also alleviate this pain.
Hey, hi. Thank you for the question. Uh, the thing is that let's say if we have abundant memory, then we are considering debloating when there is more memory pressure. If there is no memory pressure, then it's like the workloads, the processes that they can utilize the system resources. But there are ways to manage to reduce the bloat, which are engines and FreeBSD, which I have explained in the presentation. There is also some other works, but they are static based and they are static based and they are heuristics based.
Okay, I'm looking at the clock, thinking we should finish there. Thank you very much for the talk, and we'll move to the next talk. Thanks.
Thank you. Thank you.
And, right, so our next talk is also a record.
Hello everyone, my name is Sanjin So. I recently graduated from the University of California, San Diego, where I had the privilege of
Doing this sort of thing is actually doing this sort of thing smoothly is actually really challenging. So, thank you very much to the tech team who are making this happen. All right, I'll just introduce the talk while we're getting it finalized there. The next talk will be on the subject of compiler-assisted crash consistency for PMEM. And the first speaker who we just heard there is from the University of California, San Diego, Yoon Jun So.
My name is Hyunjin So. I recently graduated from the university. University of California, San Diego. Hello everyone, my name is Hyunjin So. I recently graduated from the University of California, San Diego, where I had the privilege of being advised by Professor Jijin Zhao. Unfortunately, I wasn't able to attend in person today due to a conflicting schedule with my commencement ceremony. I would have greatly appreciated the opportunity to present this work in person. Today, I'm excited to share our research on compiler-assisted crash consistency for persistent memory. This work tackles one of the most enduring challenges in the field of persistent memory, ensuring reliable crash consistency. Storage technology has been developed from block-based storage devices into byte-adjustable storage devices such as PMEM, memory semantic SSDs, and CXL SSDs. The key differences lies in the update granularity. Traditional block-based devices must overwrite the fixed-size block, resulting in easier atomic updates through additional layer of indirections. With the memory semantic as access to non-volatile storage, we need a more lightweight way of reliably persisting data. To be specific, PMEM is a byte-addressable storage that combines the benefit of DRAM and SSDs, showing near DRAM performance with non-volatility. However, PMEM introduces additional challenge to the software stack, imposing additional overhead for crash consistency or writing additional recovery code. To elaborate on the crash consistency, we present a simple example where CPU is writing a sentence, "I love research." While writing it, let's assume that a crash occurred. So in the non-volatile storage, only "I love Rizia" were persisted. Upon a reboot, CPU may be loading an incomplete sentence such as "I love Ri," "I love Riz," "I love Rissa," and so on. This is regarded as crash inconsistency. To enforce crash consistency, various techniques have been developed, including the write-ahead logging. In write-ahead logging, the CPU would first log the sentence that it will be writing. "I'm writing I love research," for example. Only when the logging is complete and persisted, the CPU would proceed with writing "I love research" in place. This process incurs high performance overhead because it not only writes the redundant information, but also the logging and in-place update has causal relationship, which means the logging must be complete before the in-place update happens. In addition to performance overhead, writing recovery code burdens the programmer. Assuming that the write-ahead logging is deployed, programmer must check whether the log has been persisted atomically, and for each case, determine how to recover the data into a consistent state. We refer recovery code to a set of logic that converts a possibly inconsistent data into a consistent state. In the recovery logic, it determines whether the log is intact. Based on the decision, it may revert to the latest consistent state as in on the logging, or reapply the committed transaction as in redo logging. After running the recovery program, the data is guaranteed to be in a consistent state. Guaranteeing the correctness of the recovery code imposes nonlinear burden to the programmer because they must ensure that both the main logic and its paired recovery code are correct. Following is the simplified logic for programming procedures. Traditionally, the programmer would check for bugs in the code and debug them until there are no more bugs, but PMEM introduces several additional steps. Unlike traditional programming procedures, PMM introduces nonlinear complications. To highlight some of the additional processes, programmers must additionally check for PMM bugs, which depends on both the main logic and the recovery code. If a bug has been found, the programmer must iterate through debugging the main logic and updating and debugging the recovery code accordingly. These additional processes are resulting to open problem and cumbersome and error-prone processes. For example, various works for PMM bug detection has been proposed, but later works identified additional classes of PMM bugs. Instead of dealing with the open problem and the cumbersome and error-prone process, we propose to automatically generate the recovery from the main logic of the program. With this approach, the PMM programming does not incur quadratic complication. There are several solutions that may indirectly mitigate the PMM programming complications, including the Intel's PMDK library, custom PMM data structure, and some prior compiler-based solutions. Each prior solution has shortcomings, including the limited programming model supported for prior recovery via resumption works, such as Clover MVM. Our proposal builds upon the recovery via resumption paradigm, where the recovery is defined as running the partially executed code to its completion. For example, given the previous example of the processing writing I love research to the storage, let's assume a crash occurred in the middle. After the reboot, the process would resume execution from the partially executed process and run to the completion. This results in a consistent data state on the storage. For a correct recovery via resumption, the key technical challenge is tracking the program state. These states should provide correct and sufficient information to answer the following questions: where to resume and from which program state to resume from. For these technical challenges, we claim that statically and systematically automated persistence is possible, or SOP for short. At a high level, we are proposing recovery via resumption with locality-aware approximate logging. As discussed, we are logging the code execution progress and state. We are approximating the program execution state by eliminating the strict ordering between the logging and the main logic. In our paper, we prove that even without this strict ordering between the logging and main logic, our approach can correctly recover to completion. Another factor that enables huge performance gain is SOP's logging storage management. SOP shows high cache locality because it statically analyzes the input program and pre-allocates memory for the logging part. This results in many cache hits and thus high performance. The key enabler is RISE, failure reentrant and idempotent section. This is a sequence of instruction without any control flow divergence within the region. For those who are familiar with LLVM, this is a basic block with the following properties. Reentrancy is when a partially executed program state can be reused to re-execute from the beginning without any side effects. Similarly, idempotency is when re-executing the same region multiple times does not incur any side effects. Here is an example of non-RISE code. In C programming language, it is I++ with some additional code that follows it. I++ can be decomposed into 3 instructions in LVM-IR: loading the value, adding 1 to the value, and storing it back to the variable I. This is an example of non-reentrant and non-idempotent code because if I++ has been successfully executed, then re-executing the code from the beginning would result in side effect or incrementing the value twice. Instead, SOP would automatically convert it into 2 rises, namely rise n and rise n+1. The 2 rises are executed back-to-back with unconditional branch, retaining to the original execution logic. Because each rise is read-only or write-only, there is no side effect of re-executing it multiple times or re-executing it from the beginning using partially executed memory state. Therefore, each rise is re-entrant and idempotent. To track the program execution status, we deploy the proposed techniques: load to persist, torn bit for store atomicity, and crash priority. These techniques collectively create a systemic way to track the execution status of memory operations within each rise. For example, if all of the memory operations within a rise has the same torn bit, then the rise has been executed atomically and should not be re-executed during the recovery. At a high level, stop involves 3 steps. First is analyzing the input program and converting it into sequence of rises. In the leftmost diagram under label before, we show the control flow of the input program. Each node is a basic block where some nodes happen to be read rise and write rise. For those that are not rise, stop converts them into a back-to-back nodes where each node is a rise. After the conversion, the second step is applying the lightweight program state tracking process for each rise. The details of each techniques is in the paper. At this point, we have the main logic program with compiler-inserted logging techniques for crash consistency. In the last step, the SOP further converts the main logic of the program that prepends the reasonable rise computation logic. The logic takes in the memory state and runs through the algorithm and branches into one of the rises. To clarify what SOP does, it takes a volatile program in LVM-IR as input. It outputs 2 executables, the crash-consistent main logic of the program and the recovery program with a new entry point that first computes the resumption location. The conversion goes through the 3 systematic processes. First, SOP preprocesses the input program so it becomes piecewise rise by inserting unconditional branches. After inserting approximate logging to track the program execution progress, the main logic is now crash consistent. By further inserting the program resumption logic, the SOP auto-generates the recovery program. For empirical evaluation of crash consistency, we developed an emulated crash framework. Given the crash-consistent program, we further modify it to have a conditional branch that may jump to the process termination instructions. The modified framework would load the environment variable of the target rise ID. When the target rise ID has been executed, the conditional branch would skip over the remaining execution and exit the program. This effectively emulates a sudden crash, leaving a partially executed memory state. Then, we run the auto-generated recovery code to recover the consistent memory state. For the litmus programs that we tested, including the I++, our recovery code successfully recovered the consistent state from all possible partially executed state. With these techniques, SOP improves the throughput by 1.8x compared to the prior state-of-the-art Clover MVM under EADR. Unlike the Clover MVM, which cannot support the lock-free data structure, SOP shows on-par performance with Mirror, a human-optimized lock-free data structure for PMM. For TATP, SOP performed 7.5x higher performance than Clover MVM. This is because TATP transactions have smaller number of load instructions. This results in smaller number of total rises and thus smaller total overhead, reaching the near theorem performance. We further evaluated the scalability of SOP. SOP showed 1.4x higher throughput than Clover MVM when varying the number of threads. For lock-free data structures, SOP showed comparable scalability to Mirror with a slightly slower performance for list data structure. To conclude, we propose SOP, which automatically generates crash recovery for PMM through compiler-inserted persistence that improves performance and supports wider programming models. Thank you, and I'm open to questions.
Let's just do a quick audio check to see if we have our speaker there. Yeah. Are you online? Can you hear us?
Yeah, I can hear you.
Terrific. Okay. I'm Steve Blackman. I'm the session chair. Now I'll just ask if we have any questions.
Hi, Eres Petrang from the Technion. There was a work by Guy Blalock and Ama Ben David and others in SPA about forming this repeatable code that you can redo when you fail and splitting the program to several of those. Are you aware of this? Or maybe I can send it to you offline.
That'd be really helpful. Thank you.
And there was also a work in P-pop where they had a bit in each word saying if it was, or a related bit in each word saying if it was already persisted or not, which also seems related, right? And I don't know.
So the bits here is not about whether it has been persisted or not. It's like sort of versioning of each cache line. So it's for every one of the cache lines that access or access within those basic blocks are identical, then it's regarded as the atomic execution of that code region. So it doesn't necessarily mean that it has been persisted or not.
Right, right. Okay, I will send you these two papers and you'll see if it's connected.
Right, thank you.
Okay, thank you.
Thank you for the great talk. And I wonder, do you know the research named Memento that presented in PLDI 2023 maybe? It also solves same problem and it uses not compiler but persistent CAS instead. And if you know it, and I wonder why there is no comparison with that framework. Thanks.
Could you repeat the name of it?
Memento.
Oh, yeah, so this work was mostly work before 2023. So for comparison onwards from 2023, I admit that it's a bit lacking, and thank you for mentioning that out.
Okay. Do we have any further questions in the room? All right. If not, let's thank the speaker for a great talk.
Thank you.
And that ends the session, and I'll hand over to our General Chair. And before I do, thank him so much for all the work he's done. Thank him on behalf of all of us for all the work he's done in making this such a really successful ISMM.
So this concludes this year's ISMM. A big thank you to Tim Harris and Onur Mutlu, who unfortunately had to change his travel plans at the last minute and is not able to be here today. But an enormous amount of work went into this program, and I think it was a fantastic program. So a big round of applause for Tim and Onur. Also, thanks for the fantastic PLDI AV team and for everyone who helped make this a success. All right, I think there's more PLDI to look forward to. And of course, hope to see you again a year from now at ISMM 2026. Tim, anything else we want to?
No, we'd love to have feedback on the event, of course. Anything we should think about doing differently 2026? Anything you've maybe seen that's worked particularly well that we should make sure we notice is appreciated in the community. So we'll figure out what the right way to do any survey is, but I'm sure Martin, myself, others who've been connected with organising the conference will be very happy to hear informal feedback if there's anything on your mind over the next few days of the conference.
Thank you, Ron.